Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap pedoman nyata, semoga Allah meridhai Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap pedoman nyata, semoga Allah meridhai Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap pedoman nyata, semoga Allah meridhai Islam Indonesia. Padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi. Syariat Islam amalan
Hello, Dr. Kushi. Hello. The microphone is working.
Yes. Hello, Prof.
Oh, I
Can
want
you hear
to
me?
talk about this one.
Yeah, I can hear you.
Okay.
How are you?
Fine, I'm fine.
Oh, very nice to see you. Thank you for accepting our
You're welcome.
invitation
Welcome, you're welcome.
to keynote address and as well as yeah. Hello, Professor Fatima.
Yes.
Maybe we will start.
Hello.
I cannot
Hello,
see him.
Professor.
I cannot see her.
Hello. Can you hear me?
I cannot see you.
Hello.
Hello.
Can you hear me?
Yes, I hear you, but cannot see you.
Oh, really?
Open your video.
Yes, maybe.
Already, I have already opened my video.
Oh.
Good afternoon, Professor.
Fatima.
Hello.
Yeah, can we start?
Yes.
Yes, time is 10. Okay.
Oh, okay.
Big screen.
Hey, nice view.
Nice view. Big screen. Nice view. Yeah.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Very good morning to everyone. The Honorable Vice Rector for Collaboration and Entrepreneurship of Universitas Islam Indonesia, Bapak Wiryono Raharjo, PhD. The Honorable Professor Muhammad Rafi bin Johan, the Director of Nanotechnology and Catalysis Research, University Malaya, Malaysia. Professor Dr. Jiban Powder, the founder of Crystal Growth Lab, Department of Physics, Bangladesh University of Engineering and Technology, Bangladesh. Dr. Suresh Sagadevan from Nanoket, University Malaya. Distinguished keynote speaker, participants, ladies and gentlemen. I am Is Fatima from Chemistry Department, Universitas Islam Indonesia. Together with Dr. Suresh Sagadivan, we are the conveners for today and tomorrow International Virtual Conference on Advanced Functional Nanomaterial and their Application 2020, jointly organized by Chemistry Department of Universitas Islam Indonesia, Nanoket University of Malaya, and also in association with Department of Physics, Bangladesh University of Engineering and Technology. It is delight and our pleasure to have all of you, the speakers and also participants in this online event. And I would like to extend our thanks to all keynote speakers from IT support from Universitas Islam Indonesia, as well as for Nanoket and also Bangladesh University Engineering of Technology. Actually, the conference objective is we know that there are advancement in functional nanomaterial research, and the application are for several areas, from the electronic sensors, medical devices, energy, etc. So in the perspective of the synthesis, characterization, and optimization for those applications, there are some functional material like graphene-based material, zirconia-based material, carbon, nanotube, and etc. So as the scientists, as material scientists, we need to share and also inspire other scientists worldwide. So that's why we conduct this online meeting with the hope that it will be benefit for all material scientists around the world. Okay, so there are keynote speakers for this There are 6 keynote speakers for this event. The first one is Professor Won Chun-oh from Mamse University, South of Korea. Professor Masaya Ichimura and also Prof. Soga Tetsuo from Nagoya Institute of Technology. Dr. Renat Witri Wahyu Lestari and Dr. Fitria Rahmawati from Universitas Negeri 11 Maret. Also, we have Professor Tofel A.M. Shed from University of Limerick, Ireland. And Alhamdulillah, until yesterday, we have more than 500 registered participants interested to join with us. And the rundown for today consists of 2 main parts. The first part is opening session, and the second part is keynote lecture from 3 keynote speakers. And okay, we will move to the opening session. We will have the speech from Mr. Wiryono Raharjo, the Vice Rector for Collaboration and Entrepreneurship (UII), inaugural address from Professor Jiban Powder, and then presidential address from Professor Muhammad Rafi. Also, we will have the keynote address from Prof. Won Chun-oh. So, for not wasting time, so I welcome Mr. Wiryono Raharjo, PhD, to give the speech. Time and screen are yours. Okay, please.
Thank you very much. Can you hear me?
Yes, yes.
Okay. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Honorable Chair of Department of Chemistry, Universitas Islam Indonesia, Prof. Fatima, honorable speakers of the conference. I'm sorry I didn't get a chance to record one by one. Honorable conveners of the conference and all participants of the International Conference on Advanced Functional Nanomaterials and their applications. Well, first of all, let us thank Allah Subhanahu wa Ta'ala for His blessing that makes us healthy in these pandemic situations. I wish this conference happens in our campus in Indonesia, so I can welcome you all to our university and the cultural city of Yogyakarta. My name is Wiryono Raharjo, as Prof. Fatima already introduced me to you. I'm the Vice Rector for Partnership and Entrepreneurships, Universitas Islam Indonesia. Let me first briefly introduce UII, the university that hosts you now. To those who are not familiar with our university, Universitas Islam Indonesia is the oldest national university in Indonesia. We were established prior to the Independence Day of Indonesia in 1945 by some national figures of Indonesia, like for instance, Dr. Muhammad Hatta, the first vice president of Indonesia. Previously, we were located in Jakarta, but when the capital city of Indonesia moved temporarily to Yogyakarta in the late 40s, we moved here as well and remains here until today. Currently, we have 5 campuses in the city, and we host around 28,000 students, ranging from diploma program, undergraduate, up to the doctoral programs. I'm not familiar with nanomaterials. I was educated as an architect, but I believe we have a common words. called design, right? One of the intention of design is to solve problems. If you agree with that, then the main question will be how can we design something using nanotechnology to fight against COVID-19. The word something will, I guess, open up interdisciplinary collaborations. I believe this is what we are going to discuss in this conference. The other thing I'd like to address is how to maintain international cooperations without physical mobility. This has been our challenge so far. Before the global lockdown, physical mobility dominates the realizations of international cooperations. Now we have to use virtual mobility mode to maintain our cooperations. And this virtual seminar is a good example of it. So I would like to thank the organizing committee, the Department of Chemistry, Faculty of Mathematics and Natural Science of Universitas Islam Indonesia, University of Malaya, Nanocat Research Center, and Bangladesh University of Engineering and Technology for making this event possible. I think this event is a good kickoff to start thinking of what further activities we can arrange to strengthen our cooperations. I guess that's all I can say to open this event. I'm sorry, I may not be able to maintain my presence in this event due to a number of other commitments today. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Pak Wing, for very interesting opening speech. So the next is the inaugural address from Prof. Jiban Poder from Bangladesh University of Engineering and Technology. So please give the speech.
Good morning, all distinguished host members, guest speakers, leading scientists, participants, research scholars, ladies and gentlemen. Good morning, Salamat Pagi, Kalai Banakam, Suprabhat, Ohayo gozaimasu. To welcome you all and to say few words about this international virtual conference on advanced functional nanomaterials and their applications as a co-organizer of this conference. So the Bangladesh University of Engineering and Technology is very happy to join this conference and to be a host as a co-host of this conference actually. This is the first time we have come forward to organize this conference in joining these three universities. Universitas Islam Indonesia, Nanocat of University of Malaya, and the Department of Physics, Bangladesh University of Engineering and Technology. Again, on behalf of these three universities, I welcome you all again. The theme of the conference is very important: advanced functional nanomaterials and their applications. We are very happy that 6 renowned scientists from different countries are joining this conference and will give the lectures in 2 days conference, and hope that our greater audience will be motivated and encouraged by their lectures on advanced knowledge in nanomaterials. Advanced functional nanomaterials are playing vital role in our lives because of their unique properties. Advanced nanomaterials are at the heart of many technological developments that find applications such as the electronic material for communication and information, biomaterials for better healthcare, sensors for intelligent environment, energy materials for renewable energy and environment, light alloys for better transportation, materials for biotechnological applications, and more. In the last few decades, there has been great and unpredicted progress in the synthesis, in the characterization, and potential applications of functional and tailored advanced nanomaterials. Advanced functional nanomaterials are suitable and unique because of their enhanced and improved physical, chemical, and functional properties. Nanomaterials include the metal and metal oxides, nanoparticles, carbon-based materials such as the single-walled or multi-walled carbon nanotubes, and graphene oxide, carbon dots, polymeric nanomaterials, biomaterials, and so on, have attracted a great deal of attention from the researchers. The rapid development of functional nanomaterials provides the possibilities of designing better and unique devices with outstanding properties. You all know that the current days are different from our usual normal life. Although nowadays, globally we are passing very hard time and struggling to survive from COVID-19, but we hope that we should overcome this crisis and hope to have the better days very soon, and we could participate physically in the conference and meet our friends in our near future. So we should not give up our scientific progress to COVID-19. So further, we hope that this virtual conference will be very fruitful, enjoyable, and memorable to all of you. And we hope that this contribution by these three universities will continue our cooperation for in near future, and definitely we can build up a good bonding actually among the faculties, among the research students and the research scholars. So we hope to see our better life and better future in near. And again, wishing you all the best and have a wonderful day. Thank you again for participating this virtual international conference.
Okay, thank you very much, Prof. Jiban. Very interesting and inspiring speech. So the next speech should be coming from Prof. Muhammad Rafi. Oh, okay. Okay. Okay, Prof. Muhammad Rafi bin Johan will give speech, but just wait, the admin will let him join. Oh, okay, already. Okay, please, Prof. Muhammad Rafi.
Bismillahirrahmanirrahim. Thank you, Mr. Chairperson, Professor Dr. Fatimah. Yeah. Assalamualaikum warahmatullahi wabarakatuh. And very good morning to everyone. Yeah. Distinguished speakers, yeah, ladies and gentlemen. First and foremost, yeah, on behalf of Nanotechnology and Catalysis Research Center, NanoCats, yeah, I'm very happy to be part of the organizing committee, yeah, for this very important conference. So let me give a salutation first. Yeah, the Honorable Dr. Wiryono Roharjo, Vice Rector of Universitas Islam Indonesia. Yeah, I'm happy to meet you. Yeah. And the co-chairperson of this conference, Professor Dr. Jiban Wada from Bangladesh University of Engineering and Technology, Department of Physics. Yeah. The convener of this conference, Professor Dr. Fatima, yeah, from Department of Chemistry, Universitas Islam Indonesia, and Dr. Suresh Sagadevan, yeah, my staff at Nanocat, yeah, Senior Research Fellow. And of course, the coordinators, yeah, from Universitas Islam Indonesia, like Gunjana Fadila, Vioyo Priyo Wicaksono, Dr. Arif, yeah, Hidayat, Imam Shahabani, yeah, and to the list of keynote speakers and participants. Yeah. And thank you for joining this very important conference, Advanced Functional Nanomaterial and their Applications after 2020. Yeah. So me as a director of Nanotechnology and Catalysis Research Center is very proud to be part of the organizing committee in NanoCat. Yeah, NanoCat is acronym for this Nanotechnology and Catalysis Research Center. We are a leading research center which is focusing on two main areas. That is nanotechnology and catalysis. In this center, we have scientists from multi backgrounds, yeah, physics, chemistry, yeah, biology, even engineering, yeah, where we are working closely together, yeah, on the topic of nanotechnology and catalysis. And this goes to into either fundamental aspects of research, and we can also go to extend our research to the application of these nanomaterials. Yeah? And also we go beyond that. We go for the prototyping and commercialization. So our scope of area, yeah, is very wide. Yeah, we cover the fundamental part and the application parts. And also we go to the real problems which is facing either by the industry or the governments. Yeah, we are working very closely to the industry to solve their problems. Yeah. So, ladies and gentlemen, and distinguished guests, yeah, this is the second conference that's partly jointly organized by NanoCats. Yeah. 2 weeks ago, we also have a conference, yeah, with Bharatatisan University from India and Material Research Society of India. This again, we show that even though we are now in the pandemic of COVID-19, where these pandemics make our life, yeah, is completely different, yeah, with a limited mobility, yeah, but yeah, the progress of science, yeah, is still continue, yeah, and it's not limited to space and time, right? Where we can go working, yeah, with a new mode, yeah, virtual conference, yeah, which is very I mean, the advantage of this conference, the virtual conference, is we have no limitation of number of participants, yeah, from the previous two international conference. I was told that the number of participants went to 100,000, 1,500 registered. And today, like what Prof. Fatima mentioned, around 500 participants is already registered. And this is very fantastic because if you have a face-to-face conference, yeah, we are bounded by the limiting factor. Yeah, for example, if you want to have 500 participants, we have to rent a very big auditorium. Yeah, yeah, to accommodate all these participants, and we have to book them their rooms. Yeah, and have to give them their food and so on. But for a virtual conference, that is not big things. Yeah. So this is a good thing for this virtual conference. Yeah, since it can cover more wider participants. Yeah, and the participant doesn't pay anything, yeah, for this conference. Yeah, that's good. Yeah. So again, if from the last conference, we involved two countries, India and Malaysia. But today, the countries are increasing, yeah, from 2 to 3. We have Bangladesh, we have Indonesia, and we have Malaysia. So this shows that how the science, yeah, can be progress, yeah, without any limitations, yeah, and restrictions. Yeah. So inshallah, I hope Dr. Suresh can organize another conference in the next 2 weeks, involve more countries, yeah, and the science can be progress and goes into more participants, yeah, and others. So, ladies and gentlemen, distinguished guests, yeah, the nanomaterial is a very important, yeah. Of course, if you look at the materials at the nanoscale, their properties are very different. Yeah? For example, if you synthesize the materials towards a nanoscale, their strength, their mechanical strength, their optical properties, yeah, their electrical properties, magnetic properties are very big different compared to their counterparts, yeah, at the micron level. For example, activated carbon at the micron scale are less stronger compared to carbon nanotube, yeah, at the nanoscale. And graphene, for example, their strength are much more stronger compared to steel. Yeah. So this is a very important character that can be fully utilized, yeah, by the industry. Yeah, instead of we are using steel, we can use graphene, for example. Yeah? And again, the scientist is not stopping at producing nanomaterials. Sometimes we have a problem, for example, to make a composite materials. Yeah? So therefore, we have to do some modification on the surface of the nanomaterial. Of course, because the nanomaterial, their surface area is bigger compared to their volume. So therefore, they have more surface energy, yeah, compared to their volume energy. And at the surface, they are very active. Yeah? So we have to do some modification on the surface of the area by using functionalization. Yeah? So we functionalize the surface, yeah, by using many chemicals like formic acid, carboxylic acid, or nitrogen, for example, just to make this surface, yeah, accommodate with the other materials. So therefore, we can do modifications, yeah, by doing functionalization, yeah, on the surface of the materials. So therefore, in general, if we really clearly understand what is our problems, yeah, and we can solve the problems, yeah, by producing material at the nanoscale. And if that problem is not solved at that level, we can do modification at the surface by functionalize the surface. So so that is the strategy, yeah, that the scientists, yeah, is using at the current moments, yeah. And my belief that, yeah, we have a very well-known speakers today and tomorrow, and I hope that, yeah, all the participants, yeah, will get a very benefit, yeah, from the knowledge that being delivered by the professors, yeah, with their respective area. And as a director of NanoCat, yeah, it's my sincere appreciation to the organizer and to the participants, yeah, because for joining this conference. And I hope that, yeah, yeah, and I invite all of you, yeah, to come to Malaysia, yeah, to come to Nanocat, and we can do a very good science in Nanocat. We can produce a very good result, and we can produce a paper which can publish in a very high impact journal, and we can translate the results, yeah, into commercialization prototypes, and we can also solve the industrial problem. And at the end of the day, yeah, our scientific contribution will give benefit to the countries, yeah, to the human population, and to the rest of the world. It's my prayer that, yeah, may Allah Ta'ala, yeah, will bless this conference. And my apology for the organizer for not able to follow this conference entirely, because I have another meeting after this. Yeah, I'm sorry for that. Yeah, but inshallah I will go into the YouTube after this, yeah, to see the presentation. Again, thank you for the organizer. Thank you, Prof. Fatima, for inviting me to give the presentation address. Thank you, Dr. Suresh, yeah, again for inviting me. And thank you. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Thank you very much.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Prof. Muhammad Rafi, for speech, support, and also interesting remark. Then we will have the keynote address from Professor Won Chun Oh. Okay, screen is yours, Prof.
Is it okay? Microphone is okay?
Okay, please, Prof.
Okay, thank you very much. Thank you. Good morning, everybody. Good morning, ladies and gentlemen. I am very happy to join this message to give a message to all of attendees on this conference. I just say about congratulations on this conference. Due to the worldwide coronavirus pandemic and the lockdown state, all of the exchange programs are locked down too. First time, many thanks to conference chairman, Modi, Lapivin, Johan, and the co-chairman, Jivan Fodo, and the conference organizer is Petmash and Dr. Shleshi. Thank you very much. And also all of supporting all of program arrangement and invitations of speakers are good. Thank you. Thank you very much. And I miss visiting Malaya University and miss Islam University. I hope to visit your university in the future. And another one is because this coronavirus pandemic state, all of worldwide state are locked down and decoupling. So we want and we have to go to exchange program in terms of academic field and the research field, student field in the future. So if anybody want to the co-work and visiting scholar with my group and any other group, everybody and every time welcome to my group. And finally, I hope you enjoy this conference and yourself. And finally, again, many thanks to all of speakers and attendees. I hope this conference successfully finished. Thank you very much.
Okay, thank you very much, Prof. Won Chun Oh. So the last speech for this opening is coming from Dr. Suresh. Please, Dr. Suresh. I can't hear you.
Now it's audible.
Yeah, audible.
Okay. Uh, Very good morning to all of you, and warm greetings on behalf of Department of Chemistry, Universitas Islam Indonesia, and Nanotechnology and Catalyst Research Center, University of Malaya, in association with Department of Physics, Bangladesh University of Engineering Technology, Bangladesh, are organizing an international virtual conference on advanced functional nanomaterials and their application during 9 and 10 July 2020. Due to the lockdown, academic programs also hampered. In such situations, we are arranging an international virtual conference on advanced functional nanomaterials and their application. COVID-19, the virus spreading all over the world. It is time to save our lives, protect yourself by taking essential precautions, and be a healthy person. The world is full of diamonds and gems, and we are having some of them here today at Build This event. With this note, I would like to give my artist welcome to our resource person and participants with great joy and immense happiness. On behalf of ICA FNTA 2020, it's my pleasure to welcome you all for today's event, International Virtual Conference on Advanced Nanomaterial and their applications. I feel honored and privileged to deliver the conclusion for the inauguration. A leader is someone who creates an event, but team members essentially bring life to it. It was dedication and enthusiasm of our chairperson, Professor Mohammad Rafiq bin John, Director, NanoCat, University of Malaya, Malaysia, co-chairperson, Professor Jipan Bodar, Professor Department of Physics, Bangladesh University of Engineering Technology, Dhaka, the convener, Professor Dr. Fatima, Professor, Material for Energy and Environment Research Group, Department of Chemistry, University of Islam Indonesia, and organizing member for the constant support, guidance, and encouragement and gracious participation in this inaugural function. This determination is commendable, and it's their hard work to organize this conference, which would be a huge success. I extended my sincere thanks to Professor Won Chan Ho, Department of Advanced Material Science Engineering, Anseo University, South Korea, for his kind participation in the inaugural function and his wonderful keynote address. I would like to express my thanks to Briano Vice Lecturer for Collaboration and International Affairs, University of Islam Indonesia, for his kind presence in the inaugural function and welcome address. On behalf of ICA FNTA 2020, we sincerely thank Chief Guest for kindly accepting our invitation and gracing the inaugural function. We would also like to acknowledge our esteemed speakers who took the time out of the busy schedules and showered us with their pearls of wisdom and knowledge. I'm very much thankful to International Information Center and International Affairs, Universities of Islam Indonesia, for their continuous support and advice, which have greatly helped towards the successful organization of this conference. I take this opportunity to record my sincere thank organizing members of ICA FNTA 2020 for their valuable technical support in time and help. Behalf of ICA FNTA 2020 and on my behalf, I extend a very hearty vote of thanks to all invited speakers from various countries for gracing your important work and sharing with us your findings and opinions today. I'm very much happy to share with you in the conference we received more than 500 participants from the faculty, research scholars, and students from various institutions in all over the world. I thank all the participants supporting this international conference. Before I close, I would like to thank each of you for attending this conference and sharing your expertise with our gathering. I hope that you all enjoy, share, and acquire more knowledge through this conference. I'm sure that the participants would come to know about the latest development in advanced functional nanomaterials and their application by attending this conference. Furthermore, let's have a special recognition to all the participants for the enthusiasm to participate. Thank you so much for being our pillars of support. Once again, I thank all your cordial cooperation. Thank you and wish you all the very best.
Okay, thank you, Dr. Suresh, for the speech. Before we move to the keynote lecture, we will have the screenshot session for our documentation. And for this screenshot session will be divided into two sessions. The first session will be the screenshot session for the speakers and also the organizer. So please open your video so the admin will take your pictures all together. Okay. Admin, please. Wait a moment, maybe 10 seconds. Wait a moment. Okay, already done. And then the second session is the speakers, the organizing committees, and also all participants. So please open your video for all participants. So the admin will take the screen of your profile. Please.
We cannot open, Prof.
Cannot open? Okay, wait, just wait. Actually already open, Pak Adam.
Still cannot.
Still cannot?
Yeah, the host.
Okay,
Maybe.
yeah, wait, Pak, wait. Okay, just wait for maybe 5 minutes to take the screenshot of the participants. Okay, also we will inform that this meeting is also available in YouTube with the host of Chemistry UII. Okay, thank you very much. So by the end of this screenshot session, so we have finished the opening ceremony for the conference. So thank you very much again for all supporting board, vice rector, and also the director of Nanocat. And thank you very much again. So we'll move to the main agenda for today, which is the keynote lectures. The first keynote lectures will be given by Prof. Won Chun Oh with the moderator of Dr. Suresh Sagadevan. Also for the second speech from Prof. Masaya Ichimura, also with Dr. Suresh Sagadevan. So please, Dr. Suresh, take your time as the moderator. And for all participants, as you have question for the session, you can drop your question in the chat, in the group chat. So the moderator will summarize your question to be answered by the keynote speaker. Okay, please, Dr. Suresh.
Thank you, Fatima. It's a time to that we can start our today's section. Now we are entering the first technical section of today based on the topic graphene semiconductors, technology towards highly improved chemicals and biosensor for common field application. The speaker for the first technical section will be Professor Won Chun Oh, Department of Physics, Material Science Engineering, Anseo University, South Korea. I take this opportunity and it's my pleasure to introduce Professor Won Chun Oh. Won Chun Oh is a full professor in Department of Advanced Materials and Engineering at Anseo University in Korea and School of Material Science and Engineering at Hanyu University of Science and Technology in China. And he is a guest professor in some of university like China, Thailand, and Indonesia. He obtained the Research Front Award from Korean Carbon Society and obtained the Youngsong Award from Korean Ceramic Society, the Excellent Paper Award from Korean Journal of Material Research, and Best Paper Award from Journal of Industrial and Engineering Chemistry for his pioneering work, and Award of Appreciation from ICA MMA 2011, ICA MMA 2014, and ICMMA 2019. He is an ICMMA committee board member and is appointed as a one of the conference chairman and local chairman from 2007 to present year. He was appointed as one of the top 100 scientists in the world at IBC UK. He is a current research field at nanostructured material such as metal nanocomposite, graphene materials, and metal nanoparticles, and their catalytic application for future energy sources and green chemical technologies. He is the author of 693 papers published in domestic and international journals, and is delivered a talk, special lecture, plenary lecture, and keynote lecture. He serves as the editor-in-chief of the Journal of Multifunctional Materials and Photoscience, Asian Journal of Material Chemistry, and advisory board member of Asian Journal of Chemistry. May I now take the pleasure of inviting and requesting Professor Won Chun Oh to deliver the lecture on graphene semiconductor technology towards highly improved chemical and biosensor for common field application. Prof, unmute your mic.
Is it okay? Microphone is okay?
Yes. Now it's clear. You can start your lecture.
Dr. Suresh, thank you for your kind introduction for me.
Yeah.
Okay. Is okay?
Yes, okay. It's clear.
Okay, thank you. Okay, today I'd like to talk about this graphene-based semiconductor technology toward the highly improved chemical and biosensors for the common field application. Okay, first time I'd like to introduce my university. So as you know, my university mainly specified in the aerospace and the aeronautic field. So here is Korea, China. I mainly normally go to China for my university because I work at AUSD in China. Normally go to China. Here is Thailand, Vietnam, and Malaysia. And here is Indonesia, India. Because I have some exchange program, I normally go to these kind of countries. So in the future, I want a little more exchange program with this kind of country and the university and any other institute. So this one is also very close to my country. They are very close to my country. Maybe it will take about 2 hours, from 2 hours to 5 hours, 7 hours, maybe. Normally, in India case, it's a little bit far from Korea, maybe 7 hours more. And also, this is my university location. After arrive at the Incheon airport, maybe it will take about 2 hours from Incheon airport to my university. It's a little bit closer. Maybe it's not far from to airport to my university region. Okay, here is my study field. In this day, in my laboratory, we mainly study about this kind of field. But in this day, we mainly study about this hydrogen evolution, CO2 reduction, and chemical and biosensor, and this ammonia reduction, and any other semiconductor field. A little more detailedly, in our research field, this is some kind of important study field. First time, this graphene study. So as you know, these graphene materials have a good physical and chemical properties, but it's a little bit expensive yet. So maybe how can he easily synthesize this graphene material, and how can he easily obtain this graphene material with a mass production? This one is also important. And also in this preparation process, this kinetic reaction kinetics and mechanism are very important. And also, second one is how these graphene materials combined with any other materials. So for the application field, but in the time, this combination and material synthesis as a composite and modification, this kind of field are also important. So for this kind of studies, we also require the study of thin film and coating technology, and sometimes we need the surface chemistry or colloidal chemistry. And finally, this electrochemistry field is also very important. So I a little more detail describing here. The first time I just point out that this photoelectrochemistry, this one is also very important. Photochemistry and electrochemistry combined together. But in this kind of study field, we can a little more detail study about this CO2 reduction or hydrogen evolution, or sometimes dye removal. And because this kind of solar cell field is also important field in our country or any other country. And finally, so as I said, this kind of graphene materials have good properties. So we want a little more expanded application field, such as this gas sensor and the biosensor and the capacitor. And this capacitor is a super capacitor, and also secondary battery. So as you know, in the future, maybe this kind of electrochemical device market will be widely expanded and expanded. So we want a little more detailedly high performance electrochemical devices. So first time, I want to talk about this particularly matter problem. So why am I suggesting about this problem? So maybe this one is one kind of suggested figure from this one. So can find this red label lesion. This label lesion is also completely polluted with these pollutant materials. So mainly we just call the PM2.5. This because this PM2.5 have a serious problem in human body, so maybe it really make a future problem in our society and any other society. As you know, China is also a large manufacturing factory. So after make so many kind of manufacturing product, and this one is also export to any other country, such as American, North America, or South America, and the European country, in the Korea case too. But in the time, so maybe we can find that so many kind of this kind of pollutant materials, or maybe this kind of pollutant material is consisted with NOx and SOx and carbon dioxide and any other gaseous material. So maybe as you know, these kind of materials have a serious problem. But how can it contact this kind of gaseous problem? So we want a little more study about this kind of sensing effect with graphene-based material. This one is one kind of photo taken by me. This one is also main China street in Beijing, and also this one is also Beijing sky. So can find that this hazy state, so not clear. So every time and every day. So maybe most of all this kind of pollutant flow in the Korea peninsula like that, and a little more is also affect to this Japan country like that. So maybe this one is also a little bit serious one. In case of pollutant materials, we have two kind of types. The first one is primary pollutant and the secondary pollutant. In case of this primary pollutant cases, this kind of materials are derived from this forest fire and volcano and the transportation and any other chemical material and the fertilizer and the livestock and the gas, oil and gas extraction processor and the power generation plant and any other highway or building construction. But if this kind of material is burning, we have so many kind of burning method burning. So maybe really make a sulfur oxide or nitrogen oxide or ammonia and carbon dioxide. But if these kind of materials are combined with any other metallic component or any other large size particle with a chemical reaction, maybe it will make a fine dust. This one is a 2.5, PM 2.5. So, and also next one is carbon dioxide is also a serious problem. Maybe this you can also find this global warming effect because the increasing of carbon dioxide. Maybe this global can find the global warming effect. Maybe, but in the time, so most of our carbon dioxide, it also have a portion about 30% from industrial area. And also another portion is 28% from the building construction or building operation, like accommodation. And another final portion is about 22%. This one is derived from the transportation, car or airplane and any other vehicle. So, so many scientists to worry about this increasing of carbon dioxide and carbon dioxide pollution in the air. Like this one. So our main point is how can it contact, how can it sensing this kind of carbon dioxide? So maybe I think graphene is one kind of a solution material. And also second one is I'd like to talk about this sensor material, but in this day, so we want the high technology sensor materials for the quaternary industry, but this quaternary industry also related to this IoT technology. So, and also for the some kind of a measurement and the physical and chemical field, and for the measurement of for the checkup and for the sensing of disease controlling. So we need this kind of physical chemical sensor or biosensor. So for example, in case of a health sensor such as diabetes or jaundice, So how can we check about this kind of state, disease state? So maybe if you are used this kind of biosensor, so maybe we can easily check about this kind of disease effect. And also another one is, so as you know, in this day, this coronavirus widely spread in the worldwide. So, but in that time, so maybe we can also have a solution about this virus sensor or bacteria sensor. And also next one is gas sensor. As I said, the former slide, so I mainly talk about some kind of pollutant gaseous material. So how can it sensing this kind of gaseous material? And also water pollutant problem. And in the future, maybe for the artificial intelligence technology, we mainly require this kind of sensor technology. So how can it easily contact, how can it easily sensing? And also in the future, we want the development of electronic noise, how can it easily smell? So how can we distinguish about this kind of smells? And also electronic tones. And also because this kind of market is growth and growth worldwide. So maybe this also market amount maybe little more growth and growth in the future. So as I said, in the sensor is one kind of device. Maybe this device will be provided on a usable output with some kind of a response. For example, this optical signal or electrical signal or mechanical signal, or sometimes touch, or sometimes sight, or sometimes light. So today, I'll mainly talk about this gas sensing effect and biosensing effect. Further, this kind of high sensing effect will require some kind of properties such as high conductivity or easy surface modification with this graphene material, and also will require large specific surface area material. If this kind of material is developed, maybe this kind of material have a high sensing effect or better sensing effect. So in our laboratory, we mainly check about this sensing effect with this kind of technology. So maybe this one is also one kind of sensor system. And also this one is also connected with a gas chamber, located in the gas chamber. This gas chambers are located with any other gaseous materials or pollutant materials. And also this one is also this sensor also connected with this electro performance test system with a computer system together. And also this one is also, so I suggest about some kind of designed sensor system. So we have so many kind of types of sensor system like this one. This one, first one is suggested one is it's a little bit complex, but so we can also find that this exhaust gas detect the supply area, and also this one is one kind of electrolyte. So for example, this NOx gas and oxygen gas supplied to in here, but in that time, so these sensing materials are solved this kind of gaseous material, but in that time, the solved gas supplied to this electrolyte. But in that time, this, for example, this oxygen will be reacted with this nitrogen oxide like that. But in that time, it will be make up this nitrogen gas from this kind of mechanism. So we can also sense with this kind of nitrogen gas. But because it have especially require this electrolyte, so this one is not easy. Also, so for the gas sensing, so this one is not convenient one. So second one is this one is a simple one. The first one case, so can find this electrolyte, and this one is also electrolyte. This one is the insulating substance material. And this one is the active materials. after coating of these active materials on the insulating substance materials, maybe this one is connected with some kind of electrical analyzer. So maybe in that time, this some kind of gaseous material exposure to this kind of active material regions. So we can check about this this sensing effect. So another one is without this insulating substance, we can also consider directly these active materials attached with this electrode together like that. So we can also check about this sensing effect with same analyzer like that. And the final one is also, it's also a little bit complex one. And maybe I think in our laboratory, we can easily check about the sensing effect with this analyzer machine in these two kind of cases too. But in the industrial field, so maybe, so we also need a high sensing effect. And also how can it obtain this sensing effect? How can it display about this sensing effect? These kind of points are very important. So after the design, this kind of sensor system, and we also need this kind of electro circuit system. This electro circuit system is also very important. And also in our laboratory, so we mainly, so as I said, we mainly study about this graphene composite. So how can we make a graphene composite? We have so many kind of graphene composite. So binary type graphene composite and the quaternary type or any other this kind of semiconductor materials, this kind of semiconductor materials combined with the graphene material. So sometimes so conducting polymer combined together, the polypyrrole and polyurethane and any other PVDF, any other, we have also many kind of polymer material. So because we have two kind of effect, so first one is a binding effect, and the second one is a conductive effect, conducting effect. So maybe if these polymer materials combined together, so we can also find this high sensing effect. But in the same, for the synthesis of this kind of composite material, we mainly use this kind of ultrasonic method and the self-assembly method and the microwave method and any other method. We also developed this kind of easy method. So maybe sometimes, so this method approach is a little bit difficult. If this method is a little bit difficult, so maybe we can easily obtain this active material. So we want this kind of easy method and also cheap method. This one is also an important factor. This is also one kind of design the sensor material. So from this one, so we have so many kind of types of sensor material. The first time we tried to do this kind of types, but this one is also the one kind of electrode materials. This one is also insulate substrate material. But this insulate substrate materials, we have so many kind of these insulate substrate materials. So after installation of this electrode in here, because it's the platinum is also a little bit expensive, so we can be also considered to any other metallic component. If any other component materials have a good electrical conductivity, maybe it have a good lot of electrode effect. So PT and sometimes aluminum or sometimes copper and sometimes any other metallic component. So after installation, this one is directly coating with a CVD method or any other method. So why am I using this SiO to Si substrate? Because it have a good deposition effect. We mainly use this kind of substrate. So maybe if you use this CVD method in this state, maybe some amount of graphene attached on this surface. And also second one is except this vapor deposition method, we can directly coating on with the active material on this kind of substrate. So and also except this one, and we have another designed one but without sometimes without this substrate material, with this substrate material. So we can also make this sensor material with this electrode. This one is electrode, and this one is sensing active material. Or sometimes graphene, or sometimes carbon nanotube, and sometimes fluorine, and also sometimes metallic oxide. So maybe we have so many kind of target materials for this active material. This one is one kind of some kind of various types of coating materials for the test, field test. The first one is so maybe I think you can find these different two kind of color. Maybe this one is also graphene composite, and this one is this one is a graphene coated thin film, and also this one is also graphene composite coating film. Maybe mainly this also we also use this substrate. The PET polymer film it's not easy for the coating effect. This coating method is also important. So we have so many kind of coating methods. The first easy one is Dr. Blade method. This Dr. Blade. So we have any other coating method or laser ablation method, and any other coating method. And also this one is also a little bit simple one. So for the test of sensing effect, we mainly use this kind of types of the copper electrode and aluminum electrode. And also this one is also another coating example, some kind of graphene materials coated on this FTO glass, because FTO glass have good electrical conductivity, so maybe it have a good effect for those sensing test or any other test. And also this one is one kind of field test photo. Maybe after make this long size sensor like that, so we can check about the liquid acid material or liquid ammonia, or sometimes liquid nitrogen. So we can check about this kind of gaseous materials with this long size sensor materials like that. Any other part is so last time I also talked about this one is major porosity. This porosity is important. So if any kind of materials have porosity, have a good high surface area, because it have a high surface area, maybe have a good sensing effect. Maybe this surface area is also directly related to the also the amount, gaseous amount. So we require high surface area material as an active material. So for example, porous TiO2 or porous vanadium oxide, or sometimes porous composite with this TiO2 or vanadium oxide and any other metallic oxide. So aluminum oxide and SiO2. After make this porous metal oxide, or sometimes simultaneously in this preparation process, the graphene combining together. So we finally obtained the porous metal oxide combined graphene composite. So after obtained this composite material, so we can use the this kind of material as an active material. So so I suggest about this porosity factor. So first one is non-ordered porous material, and the second one is ordered porous material. But so as you know, this indium oxide case, so have a good sensing effect in the some various kind of fields. So mainly use this porous indium oxide. So maybe if this indium oxide have a high porosity effect, so can find the stable sensing effect like that. So we suggest about this kind of porous material. So in this case, so maybe we mainly synthesize the porous indium oxide graphene composite, and also after obtain this one, the second time we also combine the porous SiO2. So we finally obtained the indium oxide graphene, major porous indium oxide graphene, major porous SiO2 like that. So we checked about this TEM image or HR TEM image, the XRD. So basically, and also this one is also basic data, Raman data, DRS data, and XPS data. And also, as I said, for the check of major porosity, this nitrogen absorption isosum is also important data. So from this one, so we can also find this kind of major porosity with a high absorption effect. So I checked about this gas sensing effect in here. The first one is also cyclic voltammogram test result. So from this one, so we can also check about this sensing effect with oxygen gas or nitrogen gas or carbon dioxide gas. And also, except this kind of measurement, so we checked about this thickness effect. So maybe, so why am I suggest about this thin film or coating state? So maybe this thin film or coating state also directly relate to this sensing effect. So we checked about this sensing effect with the thickness. And also this one is also some kind of, we checked about some kind of selectivity. So maybe we just compare two kind of gaseous materials, CO2 gas and oxygen gas. So maybe in this case, from this data, we can also find this kind of materials have a higher sensing effect against the CO2 compared to this oxygen. And also, we checked about this concentration effect. And also next one is also, so I suggest about this sensing effect with a dynamic response effect. So as you know, so maybe from the this data, you can also see about this sensing effect with some kind of amount. This one is amount dependency. The first time we also gave this amount, and the second time also increased or sometimes we also stop the gas amount. So in the time, we can check about this response effect with a time condition like that. But in that time, so how this kind of, what kind of materials have a good sensing effect? If any kind of materials have a good conductivity or good affinity with electron formation on the boundary with the gaseous materials or between the gaseous materials and active materials, maybe these kind of materials have a good sensing effect. And also this one is also another example. So we suggest about another example. So this one is also polymer composite. After the synthesis about this polymer composite active materials, we check about this XRD or SEM or TEM and Raman or DRS or XPS. So why am I suggest about this DRS? So maybe this DRS or PL data also directly affect the electron combination effect. So maybe if any kind of materials have a small size band gap, maybe this one is also directly related to this response effect. So maybe this response time is a very small one. Maybe this one is also response time is also directly related to the DRS effect or peer effect. So we suggest about this DRS data with XPS together. And also another one is we also check about this oxygen or carbon dioxide and ammonia gas with a cyclic voltammogram. So maybe I think if any kind of materials have a good sensing effect, maybe this one have a large high resistance. So from this kind of data, you can also find the decreasing current density effect like that. And also we suggest about this selectivity test result in here. This one is black one is carbon dioxide and ammonia or oxygen, or this one is also concentration dependency, or this one is also resistance effect with a time condition. So you can also find this selectivity with some kind of gaseous material. And another part is also biosensing part. So this one is also different types of cell. For the sensing of biomaterials, we need these three kind of cell devices. The first one is also counter electrode and the reference electrode in the working electrode. So working electrode prepared with a kind of method. So maybe sometimes we use this kind of graphene composite. But I don't know about so what kind of graphene materials have a high sensing effect. So we everybody in my laboratory, everybody student looking for this high sensing effect. So I don't know about this what kind of materials have good sensing effect. We also need to test and test continuously about this one. So after make this electrode like that, so we can also check about this virus. So main advantage is also we can check about the real-time sensing effect. So right now we can check about this one. For example, in case of coronavirus, we can also check about the real time. And also easily check about this one without any kind of time consumption. So this kind of electrode mainly used for the sensing effect. But this one is also one kind of suggested mechanism. So as you know, but this one is also graphene material. So as I said last time, we mainly used this major process SiO2 or major process indium oxide, and mainly used the graphene polymer composite with a semiconductor. But in that time, also this one is also related to this kind of band gap energy effect, and also related to the electron transfer effect and the electron recombination effect with a small size band gap. So this one is also suggested the basic data. First one is XRD and the TEM or XPS data. And the second one is we also suggest about this current density effect with a cyclic voltammogram. This one is also we in this presentation, I mainly suggest about this E. coli effect. So maybe, so as you know, this one is also a very simple one, and also we can easily handle it. So maybe because virus material have a similar structure, so maybe so we can use this E. coli as a standard material, but it's sometimes use this without we check about this sensing effect without E. coli like that. And another one is also current effect. But so this one is also important result. But in our case, so as I said, we synthesized so many kind of different types of graphene-based polymer composite or porous composite. This one is a porous material composite. This one is polymer-based graphene semiconductor composite. This one is also different types of graphene-based polymer composite semiconductor composite materials. So can find the different sensing effect like that. So maybe from this one, so can find the different current amount. So as you know, so maybe this current amount is there directly related to this sensing effect. So maybe this one is a basic sensing data. Okay, this is a conclusion. So our works mainly tested the potential of graphene material as a supporter with some kind of metallic oxide or metallic composite, metallic semiconductor composite, in terms of gas sensing related to air pollution and bacterial sensing related to this coronavirus 19, and also this one is also highlight more potential application of graphene-based material in the field of environmental protection and biological conversion. Okay, thank you very much. Thank you, everybody. Thank you very much.
Let us thank Professor Wanchanwo.
Yeah.
For your excellent presentation.
Yeah.
Interesting topic on graphene semiconductors technology towards highly improved chemical and biosensor for common field application. Your lecture was very interesting and informative. In fact, it was the highlight of the graphene semiconductor for chemical and biosensor application. The participant who attended really enjoyed your presentation. Yeah. We appreciate you are making time in your busy schedule and deliver the lecture for us. Behalf of participant, we have some questions. Can you answer the question for participant? The first question, phosphorus-based nanomaterial can use as sensor?
Pardon, one more time. Microphone.
Yeah. Can you hear me?
Yes, hear me.
Yeah, phosphorus-based nanomaterial can use a sensor?
Yes.
Okay. And second question, is it possible that nanomaterial have 3 pores, micro, meso, and macro? If it is possible, how to make it possible?
Maybe I think it's no problem. So many types of micro nanomaterials are no problem. But important one is how can it coating? Coating effect is also very important.
Okay. And next question, what the information we can get from the graphene characterization with HRTM? Is there to analyze? Yeah.
Yes. Yes. It's a first one is some kind of semiconductor materials closely combined with a graphene as a nano size. It's important. And the second one is what kind of structure it have. So is it have a good porous structure or non-porous structure? So what kind of structure it have? So maybe from the TEM or HRTM, you can check about this kind of points.
Okay, is it possible to use a metal organic frameworks, graphene composite for sensing application?
Yes.
Hello, Prof? Hello, Prof?
Yes, sir.
Yeah, last question.
Last session. Last
question. Is it possible to use a metal organic frameworks?
Yes, it's no problem.
Graphene composite for sensing application?
Yes. Can use this one.
Okay, thank you so much, Professor.
Yeah.
I hope you can get question from the participant in your chat box. Yeah. We appreciate your time and interest to answer the participant questions. Thank you, sir, for your words of wisdom. It will be great pleasure for us to listen to you again in our future event.
Thank you very much. Thank you, Dr. Shulesi.
Oh, thank you, Prof. It's time that we start our today's second section. Let us resume towards our next technical section. It will be my honor to invite Professor Masaya Ichimura Nagoya Institute of Technology, Japan, for his visionary words in the field of electrochemical deposition of transparent p-type semiconductors. I now request Professor Jipan Boder to chair the section and introduce the speaker. Sir, unmute your mic. Unmute your mic, sir. Sir.
Hello.
Yeah.
Thank you, Dr. Suresh, for introducing me again to chair the session.
Yes.
Now we have a speaker, Professor Masaya Ichimura from Nagoya Institute of Technology, Japan. It's my great pleasure to introduce actually Professor Masaya Ichimura, who has been working in the field of compound semiconductor for last 35 years. So Professor Ichimura's expertise is in the fabrication of solar cell, gas sensors, and to explore the overall renewable energy sources. His interest is to develop the low-cost solar cells using the electro and photochemical depositions techniques for preparing the thin films. Professor Ichimura's the main contribution, actually, he developed his own method and apparatus for forming the gold plating by electrochemical photochemical deposition. That photochemical deposition technique was first introduced by Professor Masaya Ichimura in his lab. So Professor Masaya Ichimura, actually, he received many national, international awards for his scientific contributions. And so far, I know actually he has published many papers, over 150 and close to 200 maybe, including the international conference proceedings, and supervised also many PhD students. I assume maybe over the 15 minimum, maybe that number may be more. So he's also the editor of the Material Science in Semiconductor Processing. So it's my great pleasure actually, and words are very inadequate to say about his hard working, kindness, and sincerity. In fact, actually, Professor Ichimura is my mentor, and I had an opportunity to work in his lab for my postdoc research and gathered the knowledge about the thin film research. Until today, what I am continuing the thin film depositions using that the low cost technique, which I developed actually in my lab, the spray paralysis technique. So today, Professor Ichimura will talk about the electrochemical depositions of transparent p-type semiconductors. We know the importance of p-type semiconductor, and that is not easy to grow the p-type semiconductor. And I hope that our greater audience will be very happy and will be benefited out of his nice and interesting talk. And after a long time, actually, I will enjoy that the lectures in the classroom like that. The Professor Masaya Ichimura. So I am very happy to see you in our conference, and actually, and also thankful that you accepted our invitations. So we know that during the pandemic situations, we are all busy and doing our work at home or at university office room, but still our audience will enjoy your lecture. And yeah, please, Professor Masaya Ichimura.
Okay, thank you. Thank you very much. Thank you, Poda-san, for your very kind words. I hope you can hear me.
Yes.
You can hear me? Okay.
Yeah, I'm very happy to see you also.
Thank you. Okay, may I start my talk? Can you see the slide?
Yes.
Okay.
Okay.
Okay. Then I will start my talk. My talk is about electrochemical deposition of P-type transparent semiconductor. And in fact, my talk is about uh, just thin film, not nanomaterial. So I'm sorry about that. And there are many co-authors of this work paper, and the main co-authors are Ms. Koyama, Mr. Yang, and Ms. Keihe. So they are all my students. And first about transparent semiconductors. So the material semiconductors are transparent if the band gap is larger than 3 eV. And transparent material is commonly called TCM, the transparent conductive material. And we need TCM for transparent electronics. So it includes display or touch panel. To make those things, we need transparent electrode and also transparent transistor or such devices. And also we can make transparent solar cell using TCM. This transparent solar cell absorb UV light and generate electricity. So we can use this for window panel. It just absorbs UV light and make electricity. And for those applications, transparent electronics or transparent solar cell, we need thin film on transparent substrate, glass sheet or plastic sheet like that. And we need large area thin film. And there are many TCM transparent materials, and majority oxide and sulfide. There are many transparent oxide and sulfide. So and the merit is we can make polycrystalline thin film or amorphous thin film on glass or plastic substrate by various techniques. And many of oxide sulfide is it's cheap. The constituent element is abundant and not expensive. So that is great merit for transparent electronics application. And this is the example. The oxide, zinc oxide, indium oxide, tin oxide. So those oxides are called TCO, transparent conductive oxide. And sulfide, zinc sulfide is also transparent. And those materials are inherently N-type. It means it is N-type without intentional doping. It is generally considered that the N-type conductivity is due to native defect, the anion vacancy, oxygen vacancy, or sulfur vacancy. The oxygen or sulfur, those elements have a high vapor pressure. So if you make those materials at some high temperature, then oxygen, sulfur easily vaporize. So the anion vacancy generated. So because of that native defect, it becomes N-type. And in addition to that, we know good donor impurity for those materials. For example, for zinc oxide, aluminum, gallium, good donor. For indium oxide, tin is a good donor. So indium tin oxide, ITO, is the most popular material for transparent electrode. And fluorine is good donor for tin oxide, so we can make FTO. So we can make good N-type material. So the N-type material with low resistivity. Though there are many good N-type transparent material. But the P-type is the problem. It is difficult to make, much more difficult to make P-type transparent material. And in fact, the P-type wide bandgap material has been a very hot research topic since 1980. In 1980s, many people, many researchers were working on the wide bandgap material and looking for good P-type transparent material to make blue LED. So at that time, there were the red LED and green LED, but no blue. So people trying to make blue LED, and to do that, people look for a good P-type wide bandgap material. So the attention was focused on zinc oxide, zinc sulfide, zinc selenide. So many people deposit thin film of those material by MB, CBD, and try accept the doping, nitrogen, lithium. But actually they failed. They cannot make good blue LED. And as you know, in 1990, Japanese researcher, Professor Akasaki, they made blue LED based on gallium nitride, and they got Nobel Prize. So they found that the magnesium doped gallium nitride is a very good P-type wide bandgap material. So they finally developed blue LED. So now we have some good P-type transparent wide bandgap material, gallium nitride, silicon carbide, and also diamond. And we can make various device, LED, power transistor using those materials. But if we want to use those materials for electronics, we have to use single crystal. And to make single crystal, very high temperature process is needed. Okay, and those the material, single crystal of those materials are quite expensive. But for transparent electronics, for display solar cell, the film should be deposited on glass or plastic substrate. Okay, so we need large area film, and the film should be cheap for those applications. So for example, for LED, the small crystal is okay, and small expensive crystal we can use for LED. But for solar cell display, we cannot use such small expensive crystal. We need cheap large area thin film on cheap substrate. So we cannot use those materials for transparent electronics application. So still, many researchers are looking for good P-type transparent material for transparent electronics applications. And so as I said, many oxide sulfides are N-type. The majority are N-type because of anion vacancy. Okay? But some are p-type. Why some oxide, some sulfide are p-type? So this explanation is, I think this explanation is not generally accepted, but I like this explanation. Okay, those are p-type oxide sulfide. Okay, those are I think famous p-type oxide sulfide. And there's one thing common among those materials. Okay, and that is this number is the oxidation number of metal element. Okay, the copper can have oxidation number of +1 or +2. Okay, tin +4 and +4, +2 and +4, and nickel +2 and +4. So the one important point is the metal element can have two different oxidation number, oxidation state. Okay, and in those materials, the oxidation number of metal element is this, the smaller one. Okay? So in those compounds, the metal element has smaller one of oxidation number. So if the metal element has larger oxidation number, then such compounds are formed. So in such case, metal vacancy, cation vacancy is easily formed. Because, for example, consider Cu2O. In Cu2O, the copper is 1+. Okay? Then we can replace 2 copper 1+ with 1 copper 2+. Okay? We can replace 2 copper 1+ atoms with 1 copper 2+ atom. Okay? So it means we can reduce the number of metal atoms without no problem. Okay? And it means metal vacancy is easily formed. Okay? So cation vacancy is easily formed. So in such case, the dominant defect is cation vacancy, not anion vacancy, and the material becomes p-type. So that is my favorite explanation. Okay, so there are some p-type transparent materials. Okay, one is nickel oxide, okay? And another is copper compound and alloy. Those compounds are p-type, and those alloys are maybe p-type. Okay, so our group worked on nickel oxide and those copper-based alloys. And in addition to that, we recently started to work on this material, magnesium hydroxide. Okay. So in the final part of my talk, I talk about this material. And to make thin film, we use electrochemical deposition technique. That is very simple technique. We prepare water solution and put electrodes and apply some voltage. And because of electric current, the ions are reduced and the film is deposited on cathode, the substrate. So this method is commonly used for metal plating, but with proper solution, we can make oxide and sulfide by this technique. The merit is it is very simple, low-cost technique, very cheap, and we can deposit thin film in a large area. And controllability is quick. By controlling voltage, current, we can control the deposition process. But there is one demerit. Substrate should be conductive, because it should we need to flow electric current. So on glass substrate, for example, this technique cannot be used for first layer. First layer should be, for example, ITO layer should be deposited by some other technique. And for second layer, third layer, we can use this. Okay, now I show you some results of our research work. First, nickel oxide. It has a band gap of about 3.5, and it is well-known P-type oxide. So several groups fabricated zinc oxide, nickel oxide solar cell, and mostly they use sputtering. But so far, nobody tried to make such solar cell by electrochemical deposition (ECD). So we tried. ECD, electrochemical deposition of a nickel oxide, is simple. First, we make nickel hydroxide. The solution is simple. It just contains nickel nitrate and the room temperature. And then we anneal the deposited film. Then hydroxide becomes oxide. So annealing is at 400 degrees C as in air. And this is cyclic voltammogram of deposition solution. So it is basically current voltage characteristic of the solution. And we well, the deposition, the reduction reaction. So we use this negative range. And with small current, when the current is small in this range, the hydroxide OH ions are formed by this reaction from nitrate ion. The hydroxide ions are formed, and then nickel hydroxide is formed. But under this condition, the film is like this. It is white, not transparent, because the surface is very rough. If the current is larger, more than 5, then the dominant reaction is this, water electrolysis. Okay? And by electrolysis of water, the OH is formed. And also at the same time, hydrogen gas is formed. So in this condition, we can see the bubble at the cathode. So usually in ECD, such condition is avoided because this bubble, hydrogen bubble, because of this bubble, the surface may become rough. But to our surprise, under this condition, we got this. Maybe you can see nothing, but the film is very transparent, very flat. So we mainly use this condition. So this is AFM, atomic force microscopy of as deposited film. So with large current, with hydrogen gas generation, the film is flat, very flat, and with increasing deposition time, with increasing thickness, the film surface becomes even more flat. Okay. Actually, it is strange. But with small current, the film is very rough, okay? And it becomes more and more rough with increasing deposition time. So we use this large current for deposition. And after annealing, as I said, it becomes nickel oxide. So it is XRD for annealed film. And we observe one big diffraction peak. So it is, and other, those peaks are due to ITO, and one peak from the film. And this is nickel oxide 111 diffraction. So it means the film is completely oriented, no other diffraction peak. So um, the deposited film is amorphous nickel hydroxide. And after annealing, completely 111 oriented polycrystalline oxide. And this is optical transmission. It is transparent. Okay? And we can see clear absorption rate. So it corresponds to band gap of about 3.6. But if the deposition current is small, the film is rough, okay? And it is white. Okay? And we characterize the electrical property by photoelectrochemical measurement. So in this PEC measurement, we prepare electrolyte solution and put substrate. This is sample deposited film and irradiate with some light. Okay? And the light is turned on and off. And if the semiconductor electrode is irradiated, then the concentration of minority carriers are enhanced significantly. Okay, so if the film is N-type, the whole, the minority carrier concentration is enhanced. So we observe positive photocurrent. The positive current increase under illumination. So in N-type. And if the material is P-type, the minority carrier is electron. So we will see a negative photocurrent. And this is a PEC result of nickel oxide film. And we clearly see the negative photocurrent in negative range, no positive photocurrent. So it means this film is P-type. And since we got transparent P-type NIO, we fabricated this solar cell. We deposit zinc oxide on nickel oxide, also by ECD. And so this is the device structure. And this one is optical transmission of this solar cell of the two layers, nickel oxide, zinc oxide layer. So it is almost transparent in visible range. And so it is the solar cell IV characteristic. So it shows rectification. And this is, and it shows photovoltaic property. Well, the efficiency is low, but anyway, I think it is first time to fabricate this nickel oxide solar cell by ECD. Okay, next, I move to copper-based for alloy. The idea is copper sulfide is P-type, but it is not transparent. And zinc sulfide is N-type, and it is transparent. So if we mix those two materials at some composition, we may get P-type transparent alloy, copper zinc sulfide. And similarly, copper oxide is P-type and not transparent. And zinc oxide is N-type, it is transparent. So by mixing those two materials, we may get P-type transparent copper zinc oxide. So we tried this. Okay. And but for copper zinc sulfide, first copper zinc sulfide. In fact, this one we did this nearly 10 years ago. So in this talk, I only briefly talk about this. Okay? So we can make sulfide using such solution. It contains thiosulfate ion. It is sulfur source, and copper sulfate and zinc sulfate. And we can make transparent copper zinc oxide. Uh, and we deposit zinc oxide on copper zinc sulfide and make a PN junction, PN heterostructure. This is photo. A little weak color, okay? And it shows such rectification property. So this is about a copper zinc sulfide. And recently we worked on copper zinc oxide. So I show some results. So about this material, copper zinc oxide, there are some reports. Okay? Several research groups worked on this, and some groups reported successful deposition of P-type film by sputtering or spray pyrolysis, and some reported such data with if the copper concentration is larger than some critical value, it becomes P-type. But other group reported that one cannot make P-type material. Okay? The copper in zinc oxide is very deep acceptor, so the copper zinc oxide cannot be conductive. So there are such reports also. So we deposit copper zinc oxide thin film using such solution, copper nitrate, zinc nitrate. And the important point is deposition temperature. We deposited film at room temperature and 60 degrees C. And this is film composition. Okay, at room temperature, it is the copper ratio is large. This is copper to zinc ratio. So at room temperature, the copper is more than zinc. But if the deposition temperature is 60, zinc is more. The copper content is low. So at 60 degrees C, the deposition of zinc oxide is enhanced, and the copper content becomes low. And this is X-ray diffraction. So if the film is deposited at room temperature, no peak. Those peaks are just for ITO. Okay? So no peak from the deposit. Okay? So the film is amorphous. If the film are deposited at 60 degrees C, we observe peak of the film. And this diffraction peak is just the same as for zinc oxide. Okay. The film contains some copper, but the diffraction peak is same as zinc oxide. And zinc oxide peak only. And this is optical transmission data. Okay. The film is transparent. Okay. This broken line is the film for the film deposited at room temperature, and solid line is for film deposited at 60 degrees C. And so both are transparent in visible range, fairly transparent. And for film deposited at 60 degrees C, we see absorption edge, clear absorption edge here. And it seems to correspond to the band gap of zinc oxide, or close to that of zinc oxide. For room temperature deposited film, no clear absorption. But the interesting fact is the room temperature film is copper rich, but it is transparent. And it is quick measurement. As I said, by quick measurement, we can see if the film is P-type or N-type. For room temperature deposition, we observe clear negative response. It means the material is P-type. And for 60 degrees C deposited film, we observe both negative and positive response. So it means the material is intrinsic or N-type, P-type mixed. Okay. So we are considering like this. Copper zinc oxide, if it is deposited at room temperature, it is copper rich and it is amorphous and it is clear P-type. And if deposited at 60 degrees C, it is zinc rich and it is polycrystalline and it is intrinsic or PN mixed. And that is because at 60 degrees C, zinc oxide is crystallized and maybe within a deposit, zinc oxide, copper oxide phase separation occurs. So we see zinc oxide diffraction here, and we see PN mixed response. But at room temperature, the film is amorphous. It is uniform, and it becomes good P-type transparent material. So we found the amorphous copper zinc oxide is very good P-type material. We fabricated solar cells. Okay. The copper zinc oxide is deposited at room temperature. It is amorphous. And we deposit zinc oxide at 60 degrees C. It is polycrystalline. And this is IV characteristic. It shows rectification. And we also observe some photovoltaic properties. Okay. Finally, I talk about this material, magnesium hydroxide. Very recently, we started to work on this. And magnesium hydroxide is usually considered insulator, hydroxide insulator. Okay. In fact, its band gap is 5.7 about, so it is certainly large, but it is similar to diamond and gallium oxide. And now those material, diamond, gallium oxide, are used for power electronics device. Okay? Those are considered as semiconductor. Okay? So now today, its band gap is okay. It is semiconductor, we can say. Okay? And some may think this material is not stable. In fact, not stable is magnesium oxide. MgO is unstable in air. So it easily reacts with water. Okay? So it spontaneously reacts with water and become hydroxide. So hydroxide is already, the reaction is finished already. Okay? So this one does not react with water anymore. So it is okay. And if we heat up this hydroxide at high temperature in dry ambience, then it becomes MgO. But that temperature, the temperature of conversion is around 300 to 400 degrees C. So it means magnesium hydroxide will be stable at room temperature, stable in air. So it can be a wide bandgap material, okay, wide bandgap semiconductor, and of course magnesium is a very cheap, abundant element. Okay, so Mg magnesium hydroxide is very cheap and abundant element. So I think it is very good if we can use this as a semiconductor. And we deposit copper doped magnesium hydroxide by ECD. Why copper? I will explain soon. The solution is like this: copper nitrate and magnesium nitrate. And this is CV, cyclic Boltzmann gram. And this is magnesium only. And this one is with small amount of copper in the solution. So as you can see, with small amount of copper, this negative current, reduction current increase so much. So it means copper acts as a catalyst for reduction reaction for deposition. And this is film thickness. If there's no copper in the solution, nothing, almost nothing deposited. But with some amount of copper in the solution, we can make thin film. So we add copper. And this is a photo of the deposit. You can see nothing, okay? But actually there is a film here, maybe around here. So the film is very transparent. Almost we can see. Okay. And this is OJ, electron spectroscopy. This is oxygen signal, and this is Mg. And when the copper amount is large, then we observe very weak copper signal here. But for low concentration copper, it is difficult to see. So it means the copper concentration is very low. So the copper seems to act as a catalyst. Okay? And this is optical transmission. So as you can see, the film is very transparent. Okay? No, almost no absorption. And this is PEC measurement. Okay. We observe some signal. It is weak, micro, but we observe some signal. Okay. So it is N-type. So as deposited copper doped magnesium hydroxide thin film N-type semiconductor. And resistivity like this of the order of 10 to 30 ohm centimeter. It is high, but I think we can say it is semiconducting. And as I say, it is N-type as deposit before, without annealing. But if we anneal those film at 400 degrees C in air, then the signal becomes like this. So we observe negative photoresponse. So it means the film becomes P-type. The resistivity is higher, somewhat higher. Okay. So by annealing, we can make P-type semiconducting magnesium hydroxide. To consider why the conduction type change, we measure XPS. So that this one is copper XPS peak. And before annealing, the copper is we mainly see copper 1 plus peak. Okay, this copper 1 plus. And after annealing, we observe kappa 2 plus peak also. So according to those XPS data, before annealing, it is the kappa is mainly 1 plus, and after annealing, it becomes the mixture of 1 plus and 2 plus. And for further discussion, we did some first principles calculation, DFT calculation of copper in magnesium hydroxide. And we can consider two sites, atomic sites. One is here, the substitutional site. Copper is at the magnesium site here. And the other is interlayer site. Copper is in the interlayer. And according to DFT calculation, this interlayer copper is shallow donor in magnesium hydroxide. And this substitutional copper may be deep acceptor. So, and this interlayer copper is copper 1 plus, and substitutional copper is copper 2 plus. So, our results may indicate as deposited film in as deposited film, the copper is interlayer, and copper it is copper 1 plus, and it is donor, so material is entered. And after annealing, copper becomes substitutional copper, and it is 2 plus, and it is acceptor, and the material becomes beta. Now I conclude my talk. That is brief summary of our results. About nickel oxide, we can make very flat hydroxide by electrochemical deposition with large current with accompanied by hydrogen gas generation. And we fabricated this solar cell, nickel oxide based solar cell. And for copper zinc oxide, if it is deposited at room temperature, it is amorphous and seems good P-type, transparent film. And we also fabricated this copper zinc oxide based transparent solar cell. And about magnesium hydroxide, after annealing, it becomes P-type semiconductor. And I think this magnesium hydroxide is so far many people have been working on oxide, but very few people work on hydroxide in the field of electronics. In chemistry field, many people work on that, but in electronics field, almost very few pay attention to hydroxide. But this hydroxide can be interesting material. Okay, we can find some more useful material among hydroxide. So we can even consider the group of material called transparent conductive hydroxide, TCHO. And this is the main publication of this our recent publication, just recent publication. Thank you very much. Here in Japan, our life is almost normal. Okay, about the effect of corona is not so serious. Okay, so our life is almost normal. But as you know, the country border is almost closed. Okay, we can not go abroad, or we cannot accept students or guests. So okay, this online meeting is good, but I hope someday I hope someday I can meet you offline. So thank you for your attention. Now finish.
Oh, am I audible to all of you? Hello.
Yes, sir. One John off. Please open your speaker.
Yeah, is okay. Am I okay?
Yeah. Audible.
Yeah, thank you very much, Professor Masai Ichimoto-san. So it's a beautiful presentation, and you have discussed all basic and fundamentals about the all transparent thin films or transparent electronics actually. So we have a few questions from the audience. That questions actually I will tell you. One question from Shahjahan from Chittagong University of Bangladesh. Mohammad Shahjahan actually he asked, what about the sheet resistance of transparent thin films? Is it sufficient for thin film photovoltaics? The first question.
Okay.
Second question is actually.
Okay. I can see the chat. Now I can see the chat. Okay.
Yeah, please.
Okay. To make solar cell, the conductivity is, I think it is enough. Very low resistivity, very high conductivity is not necessary to make solar cell. So our film is the conductivity is enough for solar cell, but the conductivity is not enough for transparent electrode. For electrode, much higher conductivity is needed. Okay, so the conductivity is not enough for the electrode material.
Okay, and the next question actually, do we get the enough photocurrent for transparent thin films photovoltaics?
Okay, no, okay. The point is, it is transparent solar cell. Transparent solar cell means it cannot absorb visible or infrared light. Okay, so the output current is small, much smaller than usual solar cell compared with, for example, silicon solar cell. But it is as expected. Okay, so I think if the small, so actually for the transparent solar cell is like this, the output power is not enough, but still we can use it in the window panel. Okay, so there are many window panels. Okay, so we have large area, okay, for transparent solar cell, so we can get some output, and at the same time we can cut UV light. So that is the merit. Okay? It is generally so. And about our device, our solar cell, okay, the output power is not enough, surely. The result is rather preliminary, and we have to increase the output current by some orders, 2-3 orders. We should improve.
Okay, thank you. So one more question is actually from Mohammad Shahjahan. Zinc sulfide has yellow color. Do you remove that for transparency? And if you remove that color, how can you keep the unchanged band gap?
Okay.
It is actually that question is how to remove the zinc sulfide is a colored film.
Okay. Actually, zinc sulfide is transparent. I mean, if no impurity, no defect, then zinc sulfide is transparent because it has very large band gap. So I think yellow color is maybe due to some impurity or defect. So please consider that the ideally the pure zinc sulfide is transparent.
Okay, that one question from Mona Rojana Indonesia Institute of Science. And she asked actually, why does the reference electrode is located in different bath with the working electrode?
Okay. Why the reference electrode is used? Okay. The reference electrode is, may I use a PowerPoint slide?
Yes, yes, sure.
So this is the usual ECD setup, and we put substrate, okay, working electrode, counter electrode, and this is reference electrode, and the voltage is applied between working and counter, okay, and current flow between working and counter. So why reference? Because we want to control potential of the solution, and we apply voltage between working electrode and counter electrode, and we can measure voltage, but we cannot correct value, okay, apply a correct value of voltage applied between working electrode and solution. So to control deposition process, we have to control voltage applied between working electrode and solution. Okay, but if we measure the voltage between working and counter, then we will see some voltage difference between solution and counter electrode, right? Okay, there are some voltage between solution and counter electrode. Okay, so we cannot know voltage between working and solution. Okay, so we use reference electrode. Okay, there are some voltage drop between solution and reference, but it is known. Okay, it is known. So by using reference electrode,
your presentation is just so interesting. So we have many questions from the audience. So when I ask actually Professor Itamura, so Fitri Rahmawati, she asked actually, electrodeposition is much affected by the current density. Please inform the detailed parameters. And I saw nickel oxide layer is rough. Can you please say something about her questions?
Okay.
Electrodeposition is much affected by the current density.
Okay.
And she wants to know details about some parameters. Yeah, please.
Okay. Okay. Again. Again, please look at this. The solution condition is just like this. Very simple. Very simple. Very simple. And no more. And another parameter is just deposition current. Deposition current is -8. Okay, so that's all. The condition is, the solution is this, and the current is -8. Okay, the deposition current is -8, and this is very flat. The film is very flat. So the film look like this. Okay, we have the very flat, very transparent film. I hope it can be answered to the question.
Two more questions actually. Raja Kani from India, she wants to know actually what is the meaning of shallow impurities.
Okay, I'm sorry. Shallow means the impurity donor acceptor easily ionized at room temperature. The donor release electron at room temperature, then it is shallow. And if it is deep, it is not ionized at room temperature. It means it cannot release electron at room temperature. Such impurity is deep. Okay? So deep shallow means basically it means it can give it can donate a carrier at room temperature or not. That is deep or shallow. Okay. Okay.
Okay. That is the last question
Okay.
from my university,
Yeah.
and my colleague also. She asked, it is tough to achieve p-type conductivity in a native n-type semiconductor. Can co-doping solve this problem? Conductivity via co-doping by a single-step deposition process. She is the Dr. Mehnaz Sharmin from Buet.
Okay. That is, I think it is good comment. Thank you very much. Okay. Now I don't have answer. Okay. Thank you for a good comment. Yes.
Yeah. I think actually this presentation we enjoyed. Our audience also enjoyed this. After a long time, we meet each other, not physically, but via the virtual conference.
Yeah.
It is very interesting, and our organizers actually, they did very hard work actually to organize this conference, and you people are very busy in academics, we know, but even then, in spite of your busy academic program, you accepted our invitation, and we are very happy to have you in the virtual conference, and beautiful presentations, Professor Ishimura. I think there is no more question now. So hope to have you again actually in our next conference. Actually, we expect, we need actually the speakers and the all experts, professors, academicians, scientists, actually then what we can do actually during this pandemic time. So if we contribute even via the virtual conference, that our audience, our students, our research scholars, our faculty members, we all actually will be benefited out of all of your presentations. So again, I will like to thank you, Professor Masaya Ichimura, for your time to our conference, and wish you good health. And we are very happy that still we are active and we survive. So
thank you. Thank you very much for that time.
Yeah. Okay. We wish you good health to all of you. And so I will give you now the Professor Fatima actually to conduct this conference again. So thank you very much.
Okay, thank you very much, Prof. Jiban, Prof. Ichimura, also to Dr. Suresh, and also Prof. Wan Chun Oh for kind sharing and directing the session. So after this, we will have the break, and we will start again at 2:30 Jakarta time. So we will have the last speakers for today, who is Dr. Witri Rahmawati from Universitas Negeri 11 Maret. So we'll break and see you at 2:30. See you.
Thank you.
Hello, Professor Ichimura.
Hi.
So I'd like to give one kind of comment to you. So,
okay.
So anybody ask about the color change with band gap energy? Yes, if any kind of materials have a nano size, maybe this one have a colorless material. And also if any kind of materials have a nano size, it will make a small size band gap energy.
Yeah, I see. Okay. I see. Now we just make just thin film, not nanoparticles. So yes, as you said, if the material becomes nano size, its band gap will be changed. So I mean the color will be changed. Yes, as you said. But to make, now we are considering the application for the transistor or solar cell. So for such purpose, now just the continuous thin film is so that is why we mainly work on just thin film, not nanoparticle. But
And
thank you.
another
Yeah.
one is so anybody ask about this colorless solar cell, transparent solar cell?
Yeah.
So okay, as I said, so maybe if any kind of materials after make a nano size, if this one is coating on the FTO or ITO, so we can obtain this colorless transparent solar cell. This one is one kind of dye sensitive solar size.
Yeah. I see. Understood. Yes.
Yes.
For dye sensitized solar cell type solar cell. Yes. We can use nanoparticle. Yes.
Yes.
Okay,
This one is not silicon based solar cell.
Yes. Right. Yes.
Okay.
We are just doing the usual type PN junction type solar cell, but
yes.
Okay, as you said, for DSSC, yes, nanoparticle is it
Okay.
should be used. Yes.
Thank you very much.
Thank you for your question. Thank you.
Okay, you're welcome.
Hello. Can I talk with the Professor Ismura?
Yeah.
Okay. Thank you. Actually, Professor Ishimura, I just had a research in the Belgium just about on this topics, zinc sulfide, transparent solar cell. So we saw just for if you use only zinc sulfide, you can have solar band gap 3.5 electron volt, which is not enough for I think transparency, or you don't have any photocurrent, I think, or very little photocurrent. That's how we saw that if you mix to zinc sulfide and zinc selenide, you can remove the yellowish color and you can have a band gap 3 up to 3 electron volt, and you will find very little photocurrent. So that's why I asked you that zinc sulfide is yellow color, and you need to remove that yellow color by maybe mixing with the zinc selenide.
Okay.
Yes, because no one want to see this. Your window is yellow.
Okay, I think, but zinc selenide has somewhat smaller band gap than zinc sulfide. So if you mix selenide into zinc sulfide, band gap becomes smaller. Okay, you can increase the photo current of solar cell. That's okay. But about color, okay, as I said, if zinc sulfide is pure, it has no color. But sometimes it shows some color because of some defect. Defect means some defect on the surface. Maybe I'm not very sure. So I'm not very sure about the yellow color you said. Okay, but I understood about the idea of solar cell. Yes, the mixing zinc selenide. Okay, I understood your idea. Yes. Okay.
Okay, thank you.
Hello. Once again, I thank you very much for all the participants. So we have small break. So next section will be start by 2:30 p.m.
So, Dr. Suresh. So,
Yes.
So we'll meet again at 2:30,
yes,
right?
2:30. Yeah, 2:30 to 3:30. Yeah. The third section.
So,
Yes.
so this is
Now we have a break. Yeah.
we have a break, and then next
Yes.
tomorrow at what time again? Morning.
Morning 10 to 11:30, the first section.
Okay.
And second section 1:30 to 2:30.
Oh yeah.
And third section 2:30 to 3:30.
Okay. Well, still we have a participants in the
Yes.
session. That was running actually good, but only few minutes maybe interruption or some connection or poor connectivity.
Yes.
Maybe
Sometimes this happen. Yeah. Technical
but
problem.
otherwise the whole program is okay.
Yes.
In my opinion,
Yes.
I have seen that is the sound and video, everything is okay, but only few seconds maybe for.
Yes.
Yeah. What about that is recorded, the whole program?
Yes, the whole program is recorded in the YouTube. So maybe we can send the YouTube link. Okay. You can forward to students. They can enjoy.
Oh, yeah. Sure. Because that is documented, all the lectures.
Lectures,
so
yes.
we're very lucky actually that we have all the renowned professors from various universities.
Yes.
And they are very happy and willingly they have given their consent to give their lecture.
Actually, we should say sincere thanks to you, your moral support and guidance and encouragement for this conference.
No, it's okay. It's okay. Then it is our pleasure actually. What we can do actually. That is your initiative. That is the first. That your hard work, your initiative, that inspired us to join actually, and we think we can do it actually during this pandemic time.
Yes.
We cannot stop our academic activities. Whatever we have now systems, we have now Zoom, and we have all the facilities actually.
Yes, we have, yeah.
Right? So,
of course.
We can connect the people, and without any expenditure that we can carry out our virtual conferences, right?
Yes.
So that is great actually. So
thank
again,
you.
Yeah. So we'll talk to
Thank
you
so
again later, right?
Yes. Thank you so much for your great support.
Now? Now we have a break, so can I leave now?
Yeah. Again, we will meet after
again I'll join.
break. Yes.
Yeah.
After 4?
2:30. Yeah. 2:30, right?
2:30. Hello, Professor Ho.
Thank you, Dr. Fred.
Okay.
Yeah, thank you so much. Yeah. So again, we have after the small break. So next section will be at 2:30
actually
p.m.
one to know. Actually, I'm very happy to talk to you. And in the beginning, actually, you have given a beautiful slides presentations and very interesting. And thank you for our audience actually. That all the senior lecturers, the researchers, the faculty members, and they are working on this all graphene material, carbon nanotubes, and so this is very common and very potential materials. And you explained with beautiful slides, and that is.
Thank you very much.
Yeah, thank you very much actually.
Actually, Professor Jipun sir, Professor Ho is my collaborator.
I understand.
Yes.
So, okay.
Last time I visited his lab and
Okay, as I said, so if anybody want to join our group, everybody welcome to my group.
Okay. We'll do more work. Yes, better. We will do giant work.
Goes to Suresh. Actually, he connected all the people, all from different universities.
Yes.
So that is the great actually. So we are very happy that we can collaborate.
Yeah, in future we will do more things we will do. Yeah, jointly. Yeah. Okay, so can I and then we will join at 2:30. Thank you.
Again, we will meet
everyone. Yes.
Thank you very much. Okay. Can I leave?
Yes, you can leave. Prof? Yeah. Okay.
Majukan studi, giatkan bakti untuk pembangunan pertiwi. Syariat Islam amalan kita, tegakkan iman dan tauhid dengan cakap Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap pedoman nyata, semoga Allah meridhoi Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap pedoman nyata, semoga Allah meridhoi Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap pedoman nyata, semoga Allah meridhoi Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap pedoman nyata, semoga Allah meridhoi Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan pertiwi, syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakap pedoman nyata, Islam Indonesia. Padamu kami berjanji, majukan studi majukan studi, giatkan bakti untuk pembangunan pertiwi. Syariat Islam amalan kita, tegakkan iman dan tauhid dengan cakap Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan. Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan Pertiwi. Universitas Islam amalan kita, tegakkan kami berjanji, dengan cakrawala pedoman nyata, semoga Allah meridhoimu. Universitas Islam Indonesia, padamu kami berjanji, majukan studi, giatkan bakti untuk pembangunan Pertiwi. Syariat Islam amalan kita, tegakkan iman dan tauhid, dengan cakrawala
coming again to the screen to this online meeting. So in this last session, we will have the keynote lecture from Dr. Renat Witri Wahyu Lestari from Universitas Negeri 11 Maret, Indonesia. She will give the lecture on synthesis of biomorph for the application in medicine. So before we starting, I will read her curriculum vitae. So Dr. Witri Wahyu Lestari is the lecturer from Chemistry Department Universitas Negeri 11 Maret, which is located in Surakarta, Central of Java, Indonesia. And she is majored in material sciences research. There are more than 50 publications related with the synthesis of material for adsorption, as well as for catalysis and also for medicine application. I can mention some of the last publication, for example, in applied organometal chemistry with the title related with the morph-based material. Also in ACS Omega for the topic on drug release control polysulfonate. Then in the Material Research Express related with the DUT5 PG metal for the catalysis application. Also in the research on chemical intermediate related with the cisplatin modified isotonic acid as the potential in biomorphs. So Dr. Witri, are you ready for the presentation?
Yes, but I will try to find my slide first.
Okay, just start.
Wait. Gimana ini? Nggak kelihatan ya. Can you see my slide, Dr. Isfatima? Prof. Isfatima.
Not yet.
Okay.
Just click share screen, then you click on your slide so we can see your slide.
Why I cannot open this one?
Otherwise, you can send the file to us so we can show the file for you.
Wait. It is too large document.
Oh, really?
Yeah.
Okay, so for everybody, maybe you missed the first and the second.
Okay, yes.
Second session. You can also see our YouTube channel. The committee has dropped the information on the YouTube channel in the group chat. Okay. Okay.
Now you can see my screen?
Yeah.
Okay, let's start ya. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
I hope my voice is clear enough. And here I am Witri Wahyu Lestari from 11 Maret University. And thank you very much for the invitation, yeah. And also to the committee, which consists of Universitas Islam Indonesia, with the chair Professor Is Fatima, and collaborating with the University of Malaya, yeah, and also the NanoCat Association, and with the Bangladesh Science and Technology. This one is a very prestigious event for me. And thanks also for the audience for joining this international conference. First of all, the audience is not only from Indonesia, but also from another countries like from Europe and also another countries from Asia. As you know that Indonesia is very large countries here, and it is in Southeast Asian, yeah. And I am from 11 Maret University. It is quite young university actually in Central Java. And this university located in Central Java in Solo, yeah. And we have around 34,000 students and around 12 faculties. And we have also doctoral program, around 20, yeah, 20 doctoral program and 46 master program. And we have also undergraduate program, around 66 program. And for detailed information, you can see the website. And as we know that the one that very famous object in Indonesia is Borobudur. Maybe after the pandemic, everybody can visit there, or who has interested in the tourism can visit the Borobudur temple. And our university is located northwest from the Yogyakarta and also from this temple. And this my university is also very famous. I mean, the city, yeah, the city is very famous because our current president is from there. And what's interesting here is the batik that's very famous from Indonesia, also produced very large in our city, and we have many interesting objects. Yeah, that's why we have like the keyword or the spirit, the keyword like the spirit of Java. Yeah, the soul is the central spirit of the Java. And we have so many also art or dance that also interesting to be visited after the pandemic, hopefully. And now we are speaking about the research. I'm from the inorganic division, inorganic chemistry division of 11 Maret University, and my major subject is in organometallic chemistry. And we try to do some research like in innovation method of organometallic compound and how to find the synthetic and modification method in the organometallic compound also. And we try to collaborate with some groups that can that our compound can be applied in biomedicine, for example, or in catalyst, or in energy storage and conversion, and so on. This way we are open. We are very open for collaboration. And the specific or the special expertise that I have, that I major in master and in my PhD is in metal organic frameworks, or in MOF, and also in coordination polymer. What is the difference between them? I will speak later. And especially in this meeting, I will try to speak about the drug delivery system based on metal organic frameworks, or based on biomorph. We know why we need a drug delivery system, because recently the drug discovery is growing rapidly. For example, anti-cancer agent and other drug. That's why this will increase also the demand of drug-eluting medical implants. And we know also that mostly the drug consists of nonpolar group or nonpolar compound, such as ibuprofen, for example, yeah, and then also cisplatin derivative. That's why we need a drug delivery system that's safe to be used, that have low toxicity, and also has better control of drug loading capacity, and also has sustainable drug release. And in this research, there are many scientists that need to be involved, for example, from biologists and also clinician for the test, for the treatment regimen. And also in our position, or in my position, is as material scientist here. We try to find a new biomaterial that can contribute to drug delivery and control system. And another position also need like for engineer, like computational engineer, that can find the technology or simulation. And the synthesis and production start from the nanoscale and until the macro scale. Like us, like as a scientist, we try to find nanomaterials that can contribute to deliver the drug, and then after that, after we formulate the small scale, and then we can upscale to the larger scale. And for treatment or for testing, we can try with conventional release profile, or also can be setting or can be set it up to be programmed release according what the test, according to the test what we have done. For example, if we have drug that want to be released every 5 hours, for example, or every 24 hours, then we can make like a computation or a calculation before. And so far, we know that there are many biomaterial or nanoparticle system that have been studied in this field. For example, the class of dendrimer that has a very small nanoscale here, and also the class of micelle and emulsion is classified as biomaterials. And another field is in the field of inorganic material, like quantum dot, and then iron nanoparticle, gold nanoparticle, and also mesoporosilicon nanoparticle. And even zeolite also can be used as a drug delivery system. However, those are still less effective to deliver the drug. A new class of compound is called as metal organic frameworks make like a new innovation on this, because this material consists of organic linker and also the metal ion or metal oxide cluster that has high surface area or porosity, and we can tune the biocompatibility of the material also. As example here, the recently published is from the cyclodextrin based on MOF, because cyclodextrin is a class of sugar. That's why it is compatible to our body. And the porosity of this material also can be tuned according to the drug that you want to be loaded there. And before I go further about the drug delivery system, I will speak now about the MOF concept, or the MOF from the basic concept. If you are an organic chemist, we know that we have like organometallic compound that's bound around or bound via the coordination or this one coordinative bonding, which consists of organic linker that has a lone pair electron and then can coordinate with the metal ion as a nodes, and it can form one-dimensional, two-dimensional, or three-dimensional. If the structure is one or two-dimensional, it's can call as coordination polymer or coordination network. But if the compound that's formed has like cavity or porosity and form three-dimensional structure, it can be called as MOF. Because the porosity feature of this material then this kind of material can be applied in many fields. That's very interesting here, like for molecular magnet, and then gas storage and spiration, and for ion exchange, for chemical sensing, and also for biomedical application here. Here is the process or the simple description how the MOF is formed. We can see here that the zinc, for example, the zinc 2 plus, yeah, this one is from cation, and then reacted with the benzene dicarboxylic acid as a linker, and it will form MOF5 here. In this case, it's MOF5, the first MOF that published in Nature in 1999 there. And the surface area, is you can see here, is very large. It's reached up to 2,900 meters square per gram. And if we can compare with the football field, if per gram is 2,900 meters square meter, yeah, it means it's very large, the surface area. And what interesting here, that's because the ligand can be variated, and also the ion or metal ion also can be variated. This way, this material is very highly tunable. As you can see here in the bottom, for example, in the MOF5, we find the nodes form like octahedral structure with the tetrazine oxide as a secondary building unit, yeah, as metal oxide cluster. And then it will connect with the linker, with the 6 linker here, and will form like primitive cubic structure. And if we change the metal, for example, if we change with the copper ion, and then the secondary building unit will be different. This way, if we use different metal, and then the metal cluster or the nodes, the structure will be also different. This way, is this the MOF itself is very rich of geometrical modification. Yeah? And the ligand itself, what's interesting here is we can change also the ligand according what we want. I mean, but I mean, according to what we propose for the application, and we can modify the ligand by organic synthesis in this case. And about biomorph, what is interesting here, biomorph is like morph that's biocompatible for the living organism. If we study about bioinorganic chemistry, we know that there are several biometals that can be found in our body. For example, like zinc, and then calcium, iron, magnesium, cobalt, and so on. And the bioligand itself also can be found in our body, like amino acid, yeah, and the nucleic bases, and also small biomolecule, yeah, like fumaric acid, or oxalic acid, or even caffeine also can be used as a ligand here. And if we use amino acid based on glutamic acid, for example, or aspartic acid, and then there are several coordination model that can be formed if we reacted with the metal, and also if we use the derivative of histidine or methionine, yeah, also will have different geometry. And what interesting that the structure and functionality of the MOF, the combination will accumulate, and here the toxicity, as you can see in the graphic here, yeah, the degradation or the percentage of degradation is quite high after around 7 days. It means that this kind of compound also suitable bio and biodegradable. This way has a great promise to be applied in biomedical application. And here are some example of MOF or coordination polymer that consists of aspartic acid, for example, or glutamic acid, or methionine, and later can be applied in some biomedical application. And in the case of the MOF itself, it's formed through the self-assembly mechanism between the metal ion and the organic bridging ligand. And we can use this material to encapsulate the drug and also use also as drug delivery system. We can use also as bioimaging, yeah? And also biomorph drug. Biomorph drug, it's mean that the morph itself consists of, or the ligand is can be used as a drug itself, yes. And then if the morph is a cargo or as a drug cargo, it's mean that the drug can be loaded to the material and then later can be released slowly from this material. And the interaction between the drug and the morph is like a host case interaction. And then the morph has the ability to tune their structure and porosity for the better drug interaction and high loading. And how is the strategy to incorporate the biomedical relevant compound into the morph? There are 3 strategies, yeah, actually. For example, the first one is by building block approach. It's mean that we reacted directly in the metal and the organic linker that's is compatible to the body, and we can use this. And after the morph is formed, then we can use as for therapy, for example, or for imaging application. And the second strategy is by non-covalent encapsulation. It means we first synthesize the morph, or we form the morph first, and after that we load the drug, and it will form like a host case interaction. And we can also incorporate the biomedical relevant agent by covalent encapsulation. It means that we modify the linker with the bioactive compound first by organic synthesis, yeah, and after that we synthesize the morph, and that's why it's covalently linked between the drug and the compound on or the morph. For example, yeah, in this case, I will take a sample like cisplatin derivative, because cisplatin is very good for, or very active, yeah, very active for cancer treatment. And the cisplatin here is connected directly to the bifosfonate linker, yeah, and then it's coordinated to zinc cation and form like nanoporous coordination polymer or nanoscale coordination polymer. Why we modify the cisplatin into polymer? Because after we modify this cisplatin to this coordination polymer, or we link together with this bifosfonate linker, it's so less resistant to ovarian cancer cell and more stable in the blood and in the blood circulation, yeah, and the toxicity will be lower, especially to the healthy cell. And if we look into the cisplatin, the originally of cisplatin is very toxic, yeah, and very reactive. That's why it's a very good inhibitor for cell growth. Yeah, and the other derivatives like carboplatin or oxoplatin. However, the cisplatin has oxidation number 2, and this lead to the high toxicity and also resistance. It's thermally labile and highly insoluble. What innovation that can be done is to increase the oxidation number of cisplatin to be 4 to form like oxoplatin, because by increasing the oxidation number, it will lower the toxicity of the compound. Another strategy also can be done like by encapsulation, or by encapsulating the material into like host or like host material, yeah, and then can be included in polymer conjugation. Here, yeah, how is the mechanism? Maybe everybody that was studied by inorganic, you know that. For example, oxoplatin that have 4 oxidation number, first will be reduced to be cisplatin, yeah. After we, but it is, but originally in the beginning it will be oxoplatin with 4 oxidation number, but after a while, after injected in the body, it will be reduced to be cisplatin, and the chloroligand here, or the chloromyces, is very good living group and will be changed with the water, because because the component of the body mostly are water, consists of water. And then after changing with the water, at the end will interact with the cell nucleus, and inside is like nucleus basis, based in the DNA, and it will bind to this cancer cell, or the sick cell, and this way this is the mechanism how to kill the cancer cell. However, this cancer agent is very active. This way it's also will attack the healthy cell. This way to avoid this very reactive action of this compound, there are several methods that can be done here. And here I present also the platinum 4 derivative that is platinum that have been modified. Like for example, here is platinum 4 with modified with indomethacin, and also platinum 4 with ibuprofen that's conducted by Newman in 2014. And also platinum with aspirin in one side, and then also platinum with acetamide too. After we study the literature here, the cisplatin or oxaliplatin modified with the aspirin in one side has a high uptake of platinum here, and also have the apoptosis, early apoptosis higher than the other. This is our idea, because if one side of aspirin negative to cisplatin here can enhance the DNR targeting efficiency, it means will cause the increasing or will cause cytotoxicity activity increase, and then we have idea that we can modify into two sides. And then our group try to modify the cisplatin with aspirin into two sides, and we have this compound. And besides that, we also modify the cisplatin with the isonicotinic acid. And later, we hope that we will use this kind of compound to be bio linker or to be a linker in biomorph. We published this in 2019 and 2020 here. And we study also the biasplatin. We call it biasplatin because this is platin modified with aspirin in two sites, and we try to load in morph and study the slow release of this compound. This study was conducted by my master student, Ophelia, and we study from the beginning that we synthesize the cisplatin from the salt tetrachloroplatinum, and we run the reaction. So we reacted the tetrachloroplatinum with sodium or with potassium iodide to form like tetraiodide platinum, and then at the end we'll have we will have here the cisplatin, but in one side still have water, and we put excess potassium chloride, and at the end we will have cisplatin, and we oxidize with the hydrogen peroxide, and we got the oxaliplatin. And to synthesize the cisplatin modified with aspirin, we reacted first the aspirin with the DCC. DCC is an prime dicyclohexyl carboimidate, and to have like aspirin anhydride. And the aspirin anhydride were reacted with the oxaliplatin, and at the end we have this biasplatin. We published this in 2020. And for the biomorph itself, or for the drug cargo, we choose here mil 101 101 iron. Mil it's mean that Material Institute of Lavoisier. It is originally from or synthesized from the Material Institute of Lavoisier in France. And we synthesize the compound by sulfothermal method. We reacted the benzene dicarboxylate acid with iron trichloride by sulfothermal method in DMF. And then we run the reaction for around 8 hours and characterize the compound by XRD, and also characterize the surface area of the compound. And then we load the drug. It means the drug is the aspartame that we have synthesized 3 to 1 to this host material here. And the loading capacity is around 94%. And we study the release of the compound at pH 7.2 in buffer system, yeah. And you can see here the compound is has a very low solubility in water, yeah, because the buffer is in water. And we see that here that without the matrix, in this case is mil 101, the release of aspartame is around 3%. But if we put the matrix, the release is around 0.05% here. It's very low. But this one is, it means the release process is successful here, because the cisplatin itself, or cisplatin derivative, is very toxic. That's why the slower the release is, the better actually. And we study also the nanotracking analysis to know how small is the material, yeah, and to know the dispersity of the material. We test here after 1 sonication, after 1 hour sonication, the material looks homogeneous, yeah. But after 2 hours standing, we saw here is the dispersion of the material, and after 24 hours standing, we saw the material is sedimented here or precipitated here. So the solubility of the material is, or the solubility of the drug is very low here. Now I will conclude the first topic that I have delivered here. The nicoplatin, it's mean the cisplatin material with nicotinic acid can be synthesized from the oxoplatin and nicotinic acid chloride, a starting material by substitution reaction of hydroxo group in its axial position. Actually, the reaction is very simple, yeah, only one step. But our idea, maybe you can impress the reviewer. That's why they accept our paper here. And the cisplatin modified with aspirin into site, or we call it as biasplatin, was successfully synthesized from oxoplatin and aspirin anhydride. Yeah. And the release of the aspartame without loading into mil 101 iron is persistent around 3%. Yeah. But after we load in the mil 101 iron, the release achieve around 0.05% over 22 hours. It means that the significant slow release of the aspartame into mil 101 iron is only 100% compared to the aspartame without loading into the mil 101 iron. However, the result of the study can be used as a precursor linker for biomorph containing cisplatin derivative to develop an efficient anti-cancer drug. The further research will be conducted by my master student Larasati next year. And now we'll move to the other modification of biomorph. In this case, we use magnesium based on biomorph with the linker trimesic acid or benzene tricarboxylic acid, and we try to modify with the graphene oxide and with iron 3 tetraoxide here. But why actually we need to modify the morph? The first one is to increase the stability of the morph itself, and also to increase the loading capacity of the material. And besides that, actually there are many several strategies that can be done. For example, by coating the morph with the silica, for example, and also by coating with the organic polymer. It will enhance the stability and also the loading capacity of the material. And luckily that we are what we are working is already accepted in applied organometallic chemistry, and our proposed cover, yeah, front cover is accepted, yeah, and we will see maybe in the next month. And why here we choose graphene oxide? The MOF itself actually consists of polar and non-polar part. Yeah. Polar is from the metal and non-polar from the ligand. But with the addition with the graphene oxide, it will increase also the lipophilicity. That's why it will uptake the drug higher, yeah. And we put also, or we add also the with the iron oxide, iron 3 tetraoxide as a magnetic agent here to attack the drug. And the interaction with the drug and the host itself is actually like van der Waals interaction, or we can call as a non-covalent interaction. And like another interaction is like pi-base stacking, because the drug and the MOF itself has aromatic ring, yeah, and also can be occurred through the hydrogen bonding. And magnesium itself is very good metal, or more biocompatible in comparison with zinc. Yeah. That's why it is promising for the biomedical application. However, yeah, after the combination of the material, the morphology of the material, of course, will decrease. Yeah, like the crystallinity will decrease, surface area will decrease. Yeah, and we try two strategies to combine the MOF with this graphene oxide and with the iron oxide here, with ex situ synthesis and in situ synthesis. Ex situ synthesis, it means the MOF is synthesized first and then mix with this graphene oxide and with the iron oxide through the sonication. Yeah. And we sonicated, it's sonicated around 30 minutes and form material 1 in this case. And after that, we try also in situ synthesis. It means we started from the magnesium cation and also the benzene tricarboxylate acid. Yeah. We mix the magnesium ion with the magnesium salt. Yeah. In this case, I use magnesium acetate with the iron oxide, and then we dissolve in ethanol. And another vessel we dissolve benzene tricarboxylate with the graphene oxide and dissolve in ethanol. It's made like it's formed like suspension, and then we mix to suspension this one here together, and we did the reaction under sulfothermal condition around 24 hours at 190 degrees Celsius. After the material form and then sonicated, yeah, sonicated around 30 minutes. And we have here, we compare between the MOF itself, between the magnesium BTC MOF here, and with this composite material that are formed here. And for encapsulation of ibuprofen, yeah, we just mix like by using the stirrer, magnetic stirrer, and we shake, we like using shaker, yeah, to mix them. And the correlation between the matrix it means the material that we have synthesized with the drug. In this case, we use ibuprofen for a molecular model. It's 1, 2, 3, and still around 72 hours, and will form like precipitate. Yeah, it will precipitate and we wash again with the hexane. Yeah. After that, the precipitates, it consists of ibuprofen at matrix will treat at ambient condition. And the filter analyzed by UV-Vis, yeah, at lambda maximum around to 298 nanometer. Here is the loading capacity, loading experiment. And after that, we try to run the release experiment of ibuprofen from the matrix. It means the material that we combine with this drug, yeah, we put inside the buffer, use buffer pH 5 and buffer pH 7.4, yeah, and the solution there, that's the solution that's coming from this ibuprofen and matrix, yeah, we take every 12 hour, yeah, every 12 hour around 5 milliliter, yeah. And then after we took the solution, and then we put again the fresh buffer to substitute the buffer that we took for measurement. And in this case, we use also twin 980 here to be added in the solution, so the solution will be homogeneous. And we run the reaction, or we run the measurement. We run the measurement around lambda max to 194 nanometer, and then we calculate how much ibuprofen concentration that we have there, and then we can calculate the cumulative percentage of release, with this kind of formula. And about the characterization of the material, we combine, we compare between the iron oxide and also the graphene oxide, and also the standard material from the MOF. We took it from the CCDC, and then we compare the peak of the X-ray diffractogram between the synthesized magnesium BTC here, and then we compare also with material one. It's been composite material one here, and then also composite two, the synthesized in situ and ex situ, and we compare it, and we know here that the peak that appear here is from the MOF itself. The peak from the graphene oxide and from the iron trio tetraoxide only appear very small, because the addition of the material is only 100% weight here. However, the crystallinity of the material also not so high like graphene oxide. That's why the dominant peak is coming from the MOF itself. And we run also the FTIR analysis, and we can see here that from the ligand then transform to the MOF, it shows the significant shift from the 1722 and then shifted around 1623. This means this significant shift confirm the coordination bonding between the carboxylic acid from the pencentyl carboxylic acid and the magnesium ion has been formed here. And we can see also this absorption peak from the material in material 1 and material 2 also similar with the MOF itself. And we also analyze here the morphology of this material, and here we can see the SEM image and also the GM image, the combination between the MOF and also the iron trio tetraoxide, and we can see here the graphene oxide is covering the material, and the ibuprofen entrapped mostly in graphene oxide here, and the presence of the material also confirmed by the ADX analysis. It's confirmed the material consists of iron, magnesium, and then also oxygen and carbon. And the experiment for drug release from the of the ibuprofen from the matrix material, it's confirmed that at pH 7.4, the release of ibuprofen increased by around 33.3, greater than at pH 5. It's because the solubility of ibuprofen is higher at pH 7.4. However, if we compare with the ibuprofen without the matrix, it's decreased significantly here. And another innovation that we have done, we try also to innovate the synthetic method of the biomorph itself by the green synthetic method like electrochemical methods and sonochemical methods. What is the difference here? The electrochemical methods use the metal plate or the metal zero as electrodes. It means that the metal cation coming from the electrode that was oxidized, and also the time or the reaction time is more efficiently. It took only around 1.5 or 1.5 hours, and this the impurity is also can be minimized. And another method is sonochemical method. This method using ultrasonic irradiation, and the reaction can be run around 10 minutes until 60 minutes. Yeah. In comparison with sulfothermal reaction, mostly need around 12 hours minimum. Yeah. And we try to publish this in material chemistry and physics, yeah, by innovating the synthetic method, and we can say like green infusional synthesis of MOF. And we can see here that by using the different method, also we can have the different morphology of the material. As you can see here, by ultrasonic irradiation around 90 minutes, we have like cube material here and in the nanoscale region. Yeah. And we can see also here the X-ray diffractogram of the similar peak, yeah, so the similar peak. However, the crystallinity is different. Yeah, the degree of crystallinity is different here. And we try to load the matrix, yeah, with the ibuprofen as a model, as a drug model also. And we can see here the comparison between the matrix using BTG, yeah, and also the ibuprofen is optimum if we load the drug 3.3 to 1. Yeah, yeah. And we can see also here the significant release, yeah, the slow release of this compound if with the ibuprofen was unloaded, yeah, with the matrix. So the explosive release around 85.88%, but if you put the matrix, it can slow down until around 25.7%. From here, we can conclude that the first modification, yeah, the magnesium-based MOF modified with graphene oxide and also with iron 3 for oxide here, were successfully prepared by in situ or ex situ method. Yeah. And both sonochemical and sulfothermal methods saw not significant effect on the material properties. And here, after addition of the graphene oxide and the iron oxide modified into magnesium BTC, enhance ibuprofen absorption up to 94.12%. And at pH 7.4, ibuprofen release was faster than pH 5.0 due to the increased ibuprofen solubility at higher pH. And the zinc-based BTC MOF here was successfully synthesized through the electro and sonochemical methods. And the crystallinity of the material also saw high crystallinity and also stable, thermally stable up to 300 degrees Celsius. And synthesis using sonochemical methods tend to produce higher yield and also smaller size, because for biomedical application we need nanoscale or nano size of material. Yeah. And according to our study, the longer the reaction time under ultrasonic irradiation, and the larger particle size will be formed here. And about the slow release of ibuprofen, the presence of the matrix like zinc BTC here can reach the slow release, yeah, I think around slow release of the ibuprofen with, if we compare with other using zinc BTC as a matrix. I think until here I will end my presentation, and I would like to thanks to all my students that helped me to work in the lab, and also help to finish the project that I have. And about the funding, I would like to thanks to Menristek Dikti, and also to PNBP Smart University, and also to ITSF or to Indonesian Torres Science Foundation. That is my end presentation, and I am now open for question. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Very impressive presentation, Dr. Mitri. It is proven by so many questions in the group chat. You can also see there, but maybe I can read some of them because of limited time. We will see some important question. The first question is coming from Dr. Zulkarnain from Syah Kuala University, Banda Aceh, is it possible to produce MOFs via high energy ball milling method? I think it is related with the mechanochemistry, right? For the H2 storage application. And then the second question is, as we need to consider less toxic and non-toxic compound, is it easy to synthesize highly efficient biocompatible material? So just answer two questions.
Question. Yes, Pak Zulkarnain. Greeting from Solo, ya Pak Zulkarnain is my senior as I was in Dresden. It is true that MOF can be synthesized through the ball milling reaction or from the mechanochemical reaction. I also, or our group also has done some experiment in this with this kind of methods. But the weakness is if you use the mechanochemical synthesis, the quality of the MOF sometimes is not really pure. So there are still some impurities that need to be removed on the MOF that we have. But it is like even without heating, some group can produce, yeah. But mostly, yeah, in my group we try to synthesize by mechanochemical synthesis, first grinding at room temperature, and then we heat with the oven like that without solvent. Yeah, it's possible. And the second question, and we can also use for application for hydrogen storage. It is true, yeah. But first, we should purify the MOF itself, yeah, because we will find some impurity that's formed during the synthesis. And the second question, what's the second question, who is?
Second question is related, as we need to consider less toxic and non-toxic, is it easy to synthesize highly efficient biocompatible material?
About toxic and non-toxic, yeah. Toxic and toxic, actually we can design in the beginning. We choose the non-toxic metal, like what I explained before, mostly for biomedical application. And for toxic, mostly we use for catalytic. Yeah. So I mean, then we cannot predict that for non-toxic metal is easier and toxic metal is more difficult. We cannot predict that because in my experience, sometimes it is easy to synthesize, sometimes it's difficult like that.
Okay, the third question is coming from Hamishu Aliyu Mohammed from University of Malaya. What makes you choose MIL 101 and what makes it to have a very high loading capacity and low release? And based on your study, what are the major interaction? Is that covalent or non-covalent? And then another question is, what was the size of iron oxide and graphene oxide for making composition? I don't know, is it related with your topic or not? Yeah. Okay. And then from Abdul Barik from Bangladesh University, do that compound directly applicable to the hard tissue engineering?
Yeah, from the Malaya, University of Malaya. Why I choose MIL 101 iron here? Because this this kind of compound has been proved so in so many studies that this one is biocompatible and have high loading capacity. I mean, we can check from the surface area, maybe it's around more than 3,000, I think, yeah, or 200 something, or 2,000 something, yeah. Where is it? Actually, we can also use another MIL iron, yeah, like MIL 100 iron or MIL 70 or MIL 57 iron, but MIL 101 has larger porosity and larger surface area. This is the reason.
Okay.
And what else?
So Is that possible to is that applicable to the hard tissue engineering?
For applicable for what?
Hard tissue engineering. Hard
Hyd-
tissue engineering.
For hydrogen storage or for what?
Hard tissue engineering.
Tissue engineering application.
Yes.
Oh, tissue engineering application.
Yes,
Yeah.
yes.
Yes. Actually, yes. Yeah. But we should be sure that the size of the material should be nano size here. Yeah. This way there are several synthetic innovation method. Yeah, how to produce the mill 101 iron, but in nanoscale like that. One strategy that very suitable to produce one mill 101 iron is by microwave radiation reaction. Yeah, so reaction under microwave radiation like that.
Okay, maybe I can read two other question because there are so many. So I will summarize the question and send to you so we can discuss by email.
Yes.
So the other questions are, the first one is, does the crystallinity and the particle size influence the drug loading? And then how to make the nanomaterial stable in the nano size? And actually, did it have any nanoparticle size effect in the technology?
Yeah. Yes, the crystallinity will affect the what's this? The crystallinity will affect the porosity also, and also the loading capacity, because mostly if the crystallinity is higher, then the surface area and porosity are so good like that. In some cases, we have experience in the laboratorium that if we have the MOF with low crystallinity, for example, and then the quality of nitrogen sorption isotherm also not really good. That's why we try or better to have high crystallinity. And this is what we improve from the synthetic methods like that. And about the what is? I will see in the chat. I think where is the chat? Where is the chat more?
Did it have any nanoparticle size effect?
Yes, of course. The nanoparticle size has a significant effect, especially for the application, yeah. And for the in vitro or in vivo application, it will have a high effect here.
And how to make the nanomaterial stable?
How to make the nanomaterial stable? If the main material is the MOF itself, we can cover the material with silica, for example, or with organic polymer. This is to make the material stable. Also in my presentation, I have shown that why I combine with graphene oxide and also with this iron trioxide, because to increase the stability of the material.
Okay, thank you very much, Dr. Witri. I know that it is very interesting topic, so the participants enjoy your presentation very much, but unfortunately our time is limited. So thank you very much for your kind sharing and contribution to the conference for today. So ladies and gentlemen, we have finished the last session for today, but before we meet again tomorrow, there are some issues to be noted by participants. And before this, we are, as the convener of this conference, will give appreciation to all speakers and all moderators for today. So we'll send the certificate directly after this session. So for Armin, please share the certificate. Okay, this is the certificate for Dr. Renat Witri Wahyu Lestari.
Thank you very much.
Okay, and then the next certificate is to other speaker, to Prof. Won Chun Oh.
Thank you very much.
Yeah, and then the next also the certificate for Dr. Suresh Sagadevan, for you as the moderator for today's session. And then the certificate for Prof. Okay, maybe there's a trouble for appearing the slide. So okay, the next information for tomorrow, we will start the session at 10:30 Jakarta time. Okay, and admin, please share the information. We will start tomorrow with the lecture from Prof. Saku Tetsuo. And maybe we also need the correction, comments, and also issues to improvement for our conference. So please fulfill the evaluation form by clicking this address, bit.ly/evaluation AFNTA 2020. So again, thank you very much for your kind attention, and see you tomorrow.
See you tomorrow.
Yeah. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Dr. Suresh, Prof. Jiban, Prof.
Thank you. Thank you.
Yeah. I will send the certificate after this. So sorry because maybe some file cannot.
Yeah. Professor Ichimura was in the morning session, so definitely.
Yeah. But actually we have prepared the certificate.
I know you are doing very hard work.
You too.
We are very happy that all trouble you have taken, you and so it's a great pleasure to appreciate you both actually.
Yeah, thank you. Thank you.
And also this whole session you are organizing and watching all the times actually. This is the whole program.
Yeah.
Thank you very much actually.
Thank you. So because the limited room for the Zoom, it will be automatically closed at 4 p.m. Okay.
And next, definitely we'll take the group photo actually, maybe for
Yes. Tomorrow we will share and we can publish in the social media.
That is the document and
Yes.
Thank you very much.
Thank you. See you.
See you tomorrow.
See you tomorrow.